I welcome you all in this course on mechatronics. In this lecture, we are going to talk about electrical actuation systems further. Okay, so, I have named it as electrical actuation system part 2, because as I told you in my earlier lecture that electrical actuators are one of the important component of a mechatronic system. That is why I am covering it up in 2 lectures, because these actuators are easy to control. Okay. So, in my lecture on the part 1, we have seen the relays, solenoid, and the DC motors we have seen, okay, that is permanent magnet type as well as field winding. We have seen the series, shunt wound, and the compound wound motors, their characteristic. Okay. So, all those things we have seen. We will be further taking up some of the electrical actuators over here. Okay. So, let us begin with brushless permanent magnet DC motor. So, the simple DC motor, as I told you that we use brushes basically to reverse the direction of current in the armature conductor. Okay. And these brushes actually because of wear and tear, these brushes has to be periodically changed. So, there is a commutator problem in case of simple DC motor. Okay. So, people thought about a motor which is brushless permanent magnet DC motor, and now in this case of permanent brushless permanent DC motor, permanent magnet DC motor, there are sequence of stator coils. Basically, you can see A, B, C, D. Say this sequence, and then you have A, B, C, D. So, these are the sequence of stator coils, and there is a permanent magnet rotor basically. Okay. And current carrying conductor, you see the current carrying conductor in a magnetic field experiences a force basically. Okay. So, here the current is carried by stator, okay, conductor in the stator, and it is there in a magnetic field. Okay. So, it experiences a force, and from Newton's third law, the magnet will also experience an opposite and equal force, and this is the basic principle of the brushless DC motor. So, in case of brushless DC motor, basically the permanent magnet rotor rotates because of the reactive forces which are coming from the stator side. So, to switch these coils in a sequence, the switching circuits are used, and this is provided by output from 3 sensors operating through a circuit to give appropriate base current, and Hall sensors are generally used to sense the position of rotor and initiate the switching by the transistors. Okay. And Hall sensors are positions around the stator. That schematic I have not included over here. You can see some of the standard textbook, then you can see the switching with the help of transistors. Next motor which I would like to take, these are the AC motors, and these AC motors are classified as single phase motor and the polyphase motor. Single phase motors are used for the low power, whereas the polyphase motor are used for the high power. Okay. And these motor, whether it is a single phase or polyphase, they could be further classified as the induction motor or the synchronous motor based on the principle they use for the operation. Okay. These AC motors are cheaper compared to DC motor, but their speed control is difficult. Okay. So, you will find that most of the motors which are used in the general smaller applications, they are the DC motors because it is easy to control them. Okay. The speed control of AC motor is based on the provision of variable frequency supply basically. Okay. Since the motor speed is determined by the frequency of the power supply. So, now let us look at the basic induction motor first, then we will be looking at the synchronous motor. So, let us look at the induction motor first. Okay. So, in a brushed DC motor, you see electric power is conducted to the armature through brushes and the commutators, we have seen in the previous lecture. Okay. And hence these DC motors are also known as the conduction motors, okay, because the armature conductor carry the current through them. So, they are called as the conduction motor, whereas in a AC motor actually the rotor receives power by induction in contrast to the DC motor which receive power by the conduction. Okay. So, in AC motor the rotor receives power by the induction, okay, and this induction in AC motor is very similar to the secondary side of a two winding transformer which receives power from the primary. So, I hope you must have studied the transformer where you have the primary side, okay, and we have the secondary side. So, something like this it is there. Okay. So, here in case of induction motor the operation is AC motor is similar to the secondary side of a two winding transformer. In fact, an induction motor can be treated as a transformer, okay, whose primary winding is stationary, but the secondary is free to rotate. Okay. So, this way we can carry out the treatment of it. Okay. And the major difference is the air gap between the rotor and the stator through which the flux passes. Now, let us see the single phase squirrel cage induction motor. Okay. So, here you have a rotor over here, okay, and there are the rotor conductors and you have the poles basically which form the stator actually, okay, or stator forms the pole. So, the squirrel cage induction motor consists of a squirrel cage rotor made of copper or aluminum bar and that fits into the slots over here as you can see, okay, in end rings to form complete electrical circuit, okay, and there is no external connection to the rotor here. You see, I am repeating this again, there is no external connection to the rotor because here we are talking about the AC motor. These conductors are not supplied with the external power supply, okay, and the stator consists of set of windings over here as I said, okay, and when the alternating current passes through the stator winding and alternating magnetic field is produced, and because of this alternating magnetic field electromagnetic induction takes place in the rotor and an EMF is induced in the conductor of the rotor and current flows through the rotor. Okay. Thus, we have the case of current carrying conductor placed in a magnetic field. Okay. So, this is why how it is done. Okay. So, now with this induction principle, what happens, you see, initially when the rotor is stationary, okay, the forces on the current carrying conductor of the rotor in the magnetic field of the stator are such that there is no resultant torque. Okay. So, initially your rotor is not rotating. So, that is why this motor is not self starting, you need something to start an induction motor. Okay. So, devices are used with the this motor. Okay. Now, the rotor rotates at a speed determined by the frequency of the alternating current which is being applied to the stator. Next, let us look at the synchronous motor. Okay. Now, they have a stator similar to the induction motor, okay, but the rotor which is a permanent magnet. Okay. In this case, the rotor is a permanent magnet, whereas in case of induction motor, the rotor was simple conductors were there. But in case of synchronous motor, we have a permanent magnet rotor. The magnetic field produced by the stator rotates, and so the magnet rotates with it. So, here as you can see that these are the stator and this is the rotor. Now, when one pair of pole per phase of the supply with one pair of poles per phase of supply, the magnetic field rotates through 360 degree in one cycle of supply, and so the frequency of rotation with this arrangement is same as the frequency of the supply. Okay. And synchronous motors are used when we need a precise speed control, okay, when a precise speed is required, and they are not self starting, and some system has to be employed to start them. Next, let us look at the stepper motor. As the name indicates, okay, these motors moves in steps. Okay. So, they are a special type of DC motors, okay, and it can rotate in both direction and move in a very precise angular increments. Okay. Sustain a holding torque at 0 speed and be controlled with the digital circuits. It moves in very accurate angular increments known as steps in response to digital pulses sent through an electrical drive circuit. Okay. The number and the rate of these pulses actually control the position and speed of the motor shaft. Generally, step motors are manufactured with step per revolution such as say 12, 24, 72, 144, 180 and 220, and this results in say shaft angle of say 30 degree, that is 360 divided by 12. So, this is your 30 degree. So, 30 degree, 15 degree corresponding to this, 72, 5 degree corresponding to 72 steps and so on. Stepper motors are either bipolar, that is they require two power sources, or switching or a switchable polarity power source, or they are unipolar requiring only one power source. They are powered by DC sources because basically they are DC motors, okay, and require digital circuitry to produce the coil energizing sequence for the motor rotation. Okay. As we will be I will be explaining to you how we get the different steps. Okay. Okay. And feedback is not always required for control, but why we do not require feedback? Because here we make the motor rotates in a step, and many times we know that how much steps it has to rotate, and so how many pulses has to be given. Okay. But if you have provision of position sensing, then it can ensure the accuracy, okay. And they are used in low power position control application, usually less than say 1 HP or say 746 watt. They are classified as permanent magnet or the variable reluctance stepper motor. Okay. In case of a permanent magnet stepper motor, the stator consists of wound poles, as you can see over here, these are the wound poles, okay, and the rotor poles are the permanent magnet here. Okay. So, this is your rotor. And when we excite stator windings combination, the rotor moves and holds in the different position. Okay. So, as we supply the power to the different windings, okay, this rotor rotates. And in the variable reluctance type stepper motor, the working principle is that there is a ferromagnetic rotor rather than the permanent magnet motor. So, this is your ferromagnetic rotor is there, okay, and the motion and holding results from attraction of stator and rotor poles to position with minimum magnetic reluctance, okay, that allow for the maximum magnetic flux. These stepper motor can be specified by say phase, that is the number of independent winding in the stator, step angles, that is the rotor rotation for one switching change for the stator coil, and the holding torque, that is the maximum torque that can be applied to a powered motor without moving it from its rest position and reversing spindle rotation. Let us see the working principle of permanent magnet stepper motor. Okay. The motor shown has the 4 poles, stator with 4 poles. So, you can see 1, 2, 3 and 4, these are the 4 poles, and here by changing the direction of current we can change these poles basically. Okay. So, each pole is wound with field winding, the coil on opposite pair of poles being in the series, and current is supplied from a DC source to the winding through the switches, and the rotor is a permanent magnet, and thus when a pair of stator poles has a current switched on it, the rotor will move to line up with it. Let me explain this further over here. So, as we can see this figure, so suppose in this one, this is the direction of current over here. So, say this pole is north, this pole is south, and this is my permanent magnet rotor over here, and in this one this is the direction of current. So, this is north and this is south, south pole. Okay. Now, what happens if I change this direction of current over here. So, this is the configuration, okay, that is this becomes south and this becomes north, okay. Then what will happen, this south and this north will try to align, and so the rotor will be turning like this, okay, and it will be moving to this position. And in the next turn what we can do, that we change the polarity of say these poles by changing the direction of current over here. So, this becomes north and this becomes south. So, this was the earlier condition, okay, and so this will be attracted basically over here, this is already south. So, this north will be attracted over here, and there is going to be a full 90-degree rotation over here, okay. And then further if again we change the polarity like this, this becomes north and this becomes south, okay. This was the earlier one, Okay. So, again we see that this turns further from here. Okay. This been converting into the south, this will be turning over here and it will be trying to align it. Okay. So, thus the rotor rotates here in one step. You can see that there is a rotation of 90 degree. Now, let us see the variable reluctance stepper motor. So, as I said, in case of variable reluctance stepper motor, here in place of permanent magnet, we have the rotor is made of the soft steel and it is cylindrical, say with 4 poles. Okay. So, there are 4 poles and less number of poles than in the stator. So, here you can see in the stator has 1, 2, 3, 4, 5, 6 poles and the rotor has got say 4 poles. Okay. Now, when an opposite pair of winding has current switched to them, okay, the field is produced with lines of force which pass from the stator pole through the nearest set of poles on the rotor. So, it is basically something like your stretching of the thread. Okay. So, the lines of force can be considered to be rather like elastic thread, as I said, and always trying to shorten themselves, and this way the rotor will move until the rotor and stator poles line up basically. Okay. So, that way we get the rotation of the rotor. Okay. And this is termed the position of the minimum reluctance, and that is where the shortest path is there, and this stepper motor generally give step angle of 7.5 degree or 15 degree. Now, there are hybrid stepper motor which are combination of the permanent magnet and the variable reluctance basically. Okay. So, you can see here. So, there are teeth in the cap basically to provide the variable reluctances. Okay. So, basically the same principle used as the variable reluctance over here, and this is you can see the exploded view here. So, basically this is the rotor. Okay. So, you can see that the end caps over here and there are teeth over there. So, this is the hybrid stepper motor, and this combine the features of both variable reluctance and the permanent magnet motor. Okay. So, the rotor sets itself in the minimum reluctance position in response to the pair of stator coil being energized, and this is used in your computer hard disk drive. Now, let us look at the dynamic response of a single step of the stepper motor. So, if I plot say the rotation versus time. So, say if this is the step size, naturally my motor will not directly jump into this step, rather it follows this path, okay, and it tries to settle after some time on the step size. If I add some damping to it, okay, then basically these oscillations can be reduced, and so with aided damping, this is the behavior which can be obtained. Now, these stepper motor torque speed curve, if we look at basically, okay, so there are two modes, one is called the logged step mode and other is called the slewing mode. Okay. In logged step mode, the rotor decelerates, okay, decelerates and may even come to the rest between each steps. Okay. And within this region the motor can be instantly stopped or reversed without losing step integrity. Okay. And in the slewing mode, the speed is too fast to allow the instantaneous starting, stopping and reversing, because you see that this is obtained at a greater speed range. This is how this commercially available stepper motor looks like. One can usually identify the stepper motor with the so many wires over here. Okay. So, these wires usually have a certain current coding color coding being done. Okay. So, this figure shows unipolar stepper motor field coil scheme with external power transistors, as you can see over here. Okay. That must be switched on and off to produce a controlled sequence of stator polarities to cause the rotation, and this schematic corresponds to the 6 wire basically connected to the motor. So, you can see that we have 1, 2, 3, 4, 5, 6. Okay. So, yellow, red, orange, black, green and brown. So, this is the color coding done over here. Usually the second and fifth they are usually joined together internally. Okay. So, the second and fifth wires are usually connected externally as shown, and manufacturers sometimes connect them inside the motor also, in which case the motor only has the 5 external wires. The wires are usually color coded by the manufacturer to help the user make a correspondence to the schematic. Okay. And figure include common color schemes used for say 6 wire unipolar stepper motor. Yellow is coil 1, red is 1 or 2 common, orange is coil 2, black is coil 3, green 3 or 4 common and brown is coil 4. Okay. So, the most commercially available stepper motor have 200 steps per revolution in the full step mode, and are sometimes referred as 1.8 degree stepper, that is 360 divided by 200. There is a drive circuit for this stepper motor actually, and this drive circuit comes in a single monolithic IC. Okay. So, there are various brands of these drive circuits. For example, E-Lab has got ED 1200, Synetics has got SAA 1027, and Alargo Microsystem has got UCN 5804B. Okay. And these have circuits have actually the 7414 ischemic trigger, this one. Okay. Buffer to provide sharp square wave signal, that is, and 74191 up down counter, this one which provide to least significant output bit B0 and B1, and 7486 exclusive OR gates are there. Okay. So, some of these things I will be taking up in my coming lectures. Now, let us after seeing these many motors, various types of motors we have seen. So, in this lecture we have seen the AC motors and we have seen the stepper motors. Okay. So, the question is how do we select a motor? Okay. So, when we are selecting a motor for a specific mechatronic application, the designer must consider many factors. Okay. What are these factors? What speed range I am going to use for the motor? Okay. What is the torque speed variation or torque speed characteristic? My requirement is that whether I want a motor which should be reversible, and what should be the operating duty cycle for the motor, what is the starting torque for the motor, and what is the power required for the motor. Now, the torque speed curve provides answer to many questions about a motor's performance. Okay. And most of the manufacturer actually provide this torque speed characteristic with the motor, okay. And the torque speed curve displays the torque the motor can deliver at this different speeds at a rated voltage, okay. So, for example, here the motor and torque and motor speed, say this limit provides the commutation limit, driver torque speed is here and motor continuous operation boundary, this curves provide that. Then there are a list of questions that designer must consider when selecting and sizing a motor in consultation with a motor manufacturer. Okay. What could be these questions? Will the motor start and accelerate fast enough? What is the maximum speed the motor can produce? What is the operating duty cycle? How much power does the load require? What power source is available and what is the load inertia which is permissible? Is the load be driven at a constant speed? Is accurate position or speed control is required? Is the transmission or gearbox is required? Why transmission or gearbox may be needed? Many times we have the high speed motors are available, but our speed requirement may be low or torque requirement may be high. So, we need the gearbox and the transmission system such as say gears or belt you may require if your actuator is not at that particular position. For example, in case of robots, okay, many times your actuator is not at the robot joint, it is at far off place. So, you require the power to be transmitted from distance place to that particular joint. So, you require a transmission system. Okay. Next question could be, is the motor torque speed curve well matched with the load speed curve? Okay. And for a given motor torque speed curve and load line, what will be the operating speed? Is it necessary to reverse the motor? Are there any size and weight restrictions? Many times we may have the size and weight restrictions. Okay. You see in robotic application, because when we are talking about manipulator arm, okay, the arms has to carry the motor weight. So, naturally at one way the motor weight is going to be added to the arm weight. Okay. So, we have a restriction, the weight restriction. We may also have the size restriction depending on the space available. Okay. So, these are some of the questions which the designer of mechatronic system has to ask to the motor supplier. Now, for a given motor torque speed curve and a well defined load line, okay, the system settles at a fixed speed operating point. Okay. So, if I talk about the torque speed curve like this, so this is say the motor torque speed curve, okay, and this is my load line. Okay. That is how my load varies with the operating load varies with the speed. So, now we can see that there is a intersection point and this intersection point is what we call it as a operating point. Okay. And this operating point, as we will see, is self regulating. How it is self regulating? Let us see that. Okay. So, at lower speed the motor torque exceeds the load requirement. Okay. So, motor torque exceeds the load torque, and so what will happen? The system will accelerate towards the operating point. Okay. But at higher speed, if we are talking about at higher speed, the load torque exceeds the torque supplied by the motor. Okay. So, that reduces the speeds towards the operating point. Okay. So, this operating point is actually self regulating. Okay. So, the operating speed can be actively changed by adjusting the voltage supply to the motor, which in turn changes the torque speed characteristic. So, if you want further read, please refer to again the very good resource available in Bolton and Intelligent Mechatronic System, that is our book, and the one Introduction to Mechatronics by Alciator and Histan. Thank you very much. I welcome you all in today's NPTEL online certification course on mechatronics. Today we are going to talk about data presentation systems. Okay, so there are various type of there are various ways in which data can be presented, and it is important in the sense that we need to know that what is happening in the system. So, it's some sort of values of the parameters or variables which is in the form of a display. Okay. Here is the essential components of mechatronic system, as I have been discussing with you, that is actuators, sensors, sensor signal being conditioned here, then sent to the digital control architecture and the output signal conditioning, okay. And here is the graphical displays. Okay. So, I am going to talk about this today in this lecture. So, here it could be LEDs, LCDs, CRTs or any other type of display devices. Measurement system usually consists of three elements: sensors, okay, then the signal conditioners and the display, or what we call it as the data presentation elements. And these elements can be used for the presentation of data, and they can be classified basically into two types, one as the indicators and the other as the recorders. Okay. So, indicators actually gives you the instant values, instant visual indication of the sensed variable, whereas the recorder used to record the output signal over a period of time and give you a permanent record. Okay. That is there. Now, before we proceed, let us have a small discussion on the effect of measuring elements on the rest of the system, okay, and this is what we call it as the loading. So, a general point that has to be taken into account of when putting together any measurement system is the loading, okay, and it is the effect of connecting a load across the output terminal terminal of any element of a measure system. So, this is what is going to have, that is the it is the effect basically whenever I am going to connect a measuring device into a system, it is going to affect or it is going to load the system. Okay, means a very common example which many of you may be aware of is that of a voltmeter. Okay, when a voltmeter is connected across a resistor, then we effectively have put two resistors in parallel. Okay. So, basically if say I have a resistor and I put a voltmeter over here. Okay. So, basically this is what means that I am putting the two resistors in parallel. Okay. And if the resistance of the voltmeter is not considerably higher than that of the resistor, the current through resistor is markedly changed and thus the voltage measurement changes. Okay. That is there. Now, let us look at this measurement system loading a little more in the detail, and loading can also occur within a measurement system, and suppose I have got a measurement system which consists of say a sensor, an amplifier and a display device. Okay. So, here if I look at this figure, so suppose I have got a voltage source and I have resistance of the sensor is there, and say this is resistance of the input here. Okay, that is amplifier input is there. So, in this case we can see that it is basically this resistance acts as a voltage divider. So, the voltage across this one is going to be Vs times Rin by Rs plus Rin. So, this is what it is going to be there. Now, you see this voltage is getting amplified with the help of amplifier. Okay, and we get this Vd. So, this amplified value is actually the G times Vn, okay, where G is the gain, and then this Rd acts as a voltage divider for that. So, this GVin, okay, is multiplied by Rd divided by Rout plus Rd. Okay. So, if I substitute back V in over here, okay, and simplify this, this is what we get. Okay. So, we require basically R out to be very large than Rd and Rs to be very large than Rin in order to neglect the loading effect. Next, let us look at the data presentation elements. Okay. Analog and digital meters. Okay. So, the moving coil meter is an analog indicator with overall accuracy of the order of say plus minus 0.1 to plus minus 5%. The loading problem can be there because of the low resistance. The digital voltmeter gives its reading in the form of sequence of digits with accuracies as high as plus minus 0.005%. Okay. And a digital voltmeter has typically a sample rate of 3 per second and an input impedance of 100 megavolt. The principle of digital voltmeter is that basically you have the analog input and there is going to be a sample and hold, and you are going to have the analog to digital converter after the sample and hold, and of course then you are going to have the counter. Okay. So, that is going to be there. Next is the cathode ray oscilloscope, or what we call in short as the CRO. Okay. The cathode ray oscilloscope is a voltage measuring instrument which is capable of displaying extremely high frequency signals. Okay. A double beam oscilloscope has two separate traces to be observed simultaneously on the screen, and in storage of type of oscilloscope, the trace to remain on the screen after the input signal has ceased out. Okay. And the digital storage oscilloscope digitize the input signal and store the digital signal in a memory. Then let us look at the visual display unit, or the VDU, which it is called in short. Okay. So, visual display unit is used to present the output data basically. Okay. And these are two types of displays, one is the non-interlaced display and another is the interlaced display. Okay. In the non-interlaced display, the image is built by varying the intensity of the spot on the screen as each line is scanned. Okay. So, that is there, whereas in case of interlaced display, the two scans down the screen are used to trace a complete picture. Okay. And by this the effect of flicker is considerably reduced, and on the first scan all the odd number lines are traced out, whereas in the second scan all the even lines numbers are traced out. Okay. So, here this is how it is shown, the interlaced display, and this is that non-interlaced display basically. So, you have a electron beam over here, there is X flyback and there is Y flyback. The next, let us look at the build up of characters by selective lighting. Okay. So, the screen of the visual display unit is coated with large number of phosphor dots, and these dot forms the pixel. Okay. And a text character or a diagram is produced on the screen by selectively lighting these dots. Okay. So, for example, here say we have the 7 by 5 matrix of pixels. So, I have 1 to 7 rows and say 1 to 5 columns over here. So, I can get the character here as you can see that by lighting the different pixels, I can get the character say B over here. Okay. The input data to the visual display unit is usually in digital ASCII format. ASCII is short form for the American Standard Code for Information Interchange. Okay. So, for example, a 7-bit code, this is a 7-bit code, and so can be used to represent actually 2 to the power 7, that is 128 characters. Okay. And basically with the help of these 128 characters, we can write that is all the standard keyboard characters can be incorporated along with some control functions such as return. Okay. So, these things can be represented. So, this is basically as you can see how the ASCII code for the different characters basically. So, you can see the alphabets, that is A to Z. Okay. And these are the ASCII code, a 7-bit ASCII code for the different alphabet character, and here are for the numbers basically. Okay. So, 0 to 9 you have the 7-bit code over here to represent it. Now, let us look at another very popular output device, that is the printers. Okay. So, there are a number of versions of printers are commercially available, and these are say dot matrix printer or inkjet or a bubble jet printer and the laser printer. Okay. A dot matrix printer has a print head basically which consists of either 9 or 24 pins in a vertical line as shown over in this figure, and each pin is controlled by an electromagnet. Okay. So, this is how it is. So, we have the print needle over here, there is a ink ribbon, you put up paper over here. Okay. There is a return spring hammer and there is a overrun spring basically. Okay. So, this way actually when this needle impinges on this inked ribbon, you get those characters in the paper. The inkjet printer uses a conductive ink which is forced through a small nozzle to produce a jet of very small drop of ink of constant diameter at a constant frequency. Okay. And a piezoelectric crystal is used to form the drops pulse which vibrates at a frequency of around 100 kilohertz. Okay. So, you can see over here, so ink is passed from here, piezoelectric crystal is used to vibrate it. Okay. And here you get the drops basically the ink drops you get it from here, and this is the principle for the inkjet printer. Then in case of bubble jet printer, actually the bubble jet printer uses a small heater as you can see over here. Okay. In the print head with a vaporized ink in a capillary tube. So, producing gas bubble which push out drop of ink. Okay. So, basically here you have a heater, you have a ink, when the heater is not on, this is the case, and when the heater is on, the bubble is produced as over here. Okay. And this bubble is pushed into, and the vapor bubble burst and ejects into a drop. Okay. So, the two types of ejections are there, one is the charging electrode and the other is the vertical stack of nozzles. Next let us look at the laser printer. Okay. So, the basic elements of a laser printer is a drum basically this one, okay, which is coated with photosensitive materials such as selenium. Okay. And in the dark actually in the dark it has high resistance and becomes charged as it passes close to the charged wire. Okay. So, this is what is there. So, as it passes near the charging wire, it becomes charged. So, what happens actually a laser light is sent here and it goes to the rotating mirror, and it gets reflected from the rotating mirror, falls on the this cylindrical drum, and wherever the light falls, that portion of the drum actually gets discharged. Okay. So, then what happens that this drum turns basically, and there is a toner. Okay. So, this toner is conductive basically. So, the wherever it is charged actually, so that toner gets attracted over here. Okay. Then there is a corona wire basically over here, and this corona wire charges the paper actually. Okay. And when it charges the paper, then this charged paper actually gets attracted to the inkjet basically, and that ink basically gets into the paper, and then there is a fusing roller to fix the toner on the paper. Okay. So, this is how it is there. So, a light beam is used to scan, there is a 8-sided mirror, there is a toner, there is a corona wire basically which is used for charging of the paper, okay, and there is a hot fusing roller. So, currently we are able to produce 1200 dots per inch this way. Now, let us look at the magnetic recording. Okay, this is again a type of recording device, say a floppy disk and a hard disk of computer works on the concept of magnetic recording for the data storage. Okay. So, the working principle is like this. For this, a recording head which corresponds to the input signal produces corresponding magnetic patterns on a thin layer of magnetic material, and then there is a read head basically that gives output by converting the magnetic pattern on the magnetic material to the electrical signal. Okay. The system also requires a transportation system that moves the magnetic material in a controlled way under the heads. Okay. And the basic components are thin magnetic material, recording head, read head, and the transport system. So, here is the basically working principle of the recording head which has been explained. Okay. So, when the electrical signals are fed to the coil, this one which is wound round the core, magnetic flux is produced in this core. Okay. And the proximity of the magnetic coated plastic to the non-magnetic gap means that we have a magnetic coated plastic over here and there is a non-magnetic gap. Okay. And so, when this is present here basically it means that the path for the magnetic lines of flux exist through this way, and that way it magnetizes the magnetic coating which is there, okay, put in this gap. Okay. So, thus the part of the magnetic coating becomes permanently magnetized, and thus magnetic record is produced of the or rather due to the electrical input signal. And if we talk about the replay head, okay, or replay head. Okay. So, here actually the replay head uses the same mechanism basically. Okay. And here what happens if we place the magnetized coating over here, that is in the air gap, okay, then the magnetic flux is induced in this core actually. Okay. And this flux change in the core induces the EMF in it, okay, and that is wound in the coil. Okay. And so, in this coil you have the EMF produced. Okay. So, the output from the coil is an electrical signal which is related to the magnetic record which is there on the coating. So, this way it is read, and this recording of signals in digital recording involves coded combination of bits basically. Okay. And it is done with magnetism saturation in forward say represented by 0, and in reverse direction, which is represented by 1. Okay. So, the bit cell on a magnetic surface might be appear as you can see over here. Okay. And however, we must read each cell, and thus accurate timing point are needed in order to indicate clearly when the sampling should takes place. Okay. So, for reading of these each cell, we need to have the exact timing for carrying out the sampling. Now, if we are using an external clock for this purpose, okay, then there may be a small mismatch between the timing signal and the rate at which the magnetic surface is moving under the read head. Okay. And this can miss the information, or this can result in cell being missed or even read twice. Okay. So, we need to have a certain synchronization is needed between the time it is read and the time it is clocked actually, and such synchronization is achieved by using the bit cell themselves to generate the signal for taking the samples. So, the method commonly used are, I will be discussing few of these methods, and if you want to learn more, you can refer to Mechatronics by Bolton, from where you will get sufficient information. Okay. So, the next one way is the non-return to 0, or what we call it as NRZ in short, and with this system the flux is recorded on the tape such that no change in flux represents 0 and change in flux is represented by 1. However, it is not self clocking. Okay. So, you can see that here there is a flux, so it is a constant. Okay. So, and here so there is no change, so this is represented by say 0, and here there is going to be a change, so it is represented by 1. Okay. So, and this is basically magnetized and non-magnetized. Okay. This is what is represented over here. So, again this is say constant. So, again this is 1, and again so this remains over here, and then there is a change over here, so represented by 1. Okay. So, this way it can be represented. The next way is the phase encoding. Okay. And in this method the cell is split into two halves basically. One half positive saturation flux and the other half is called the negative saturation flux. Okay. And 0 means the first half bit is positive followed by the negative saturation flux, and 1 means the first half bit is negative followed by the positive saturation flux. Okay. And this the advantage for this method is that it is self locking. Okay. So, here as we can see that 0 means first half bit is positive followed by the negative. So, you have the positive negative. So, this is 0. Okay. And if it is negative followed by the positive, okay, so that is represented by 1. Okay. So, as you can see that negative followed by positive, so that is represented by 1. So, this way this can be done, and the biggest thing is that this is self clocking. Next is the frequency modulation. Okay. Self clocking and similar to the phase encoding this is, but there is always a flux direction reversal at the beginning of each cell. Okay. And for 0 bit there is no additional flux reversal during the cell, and but for 1 there is an additional flux reversal during the cell. Then let us look at the magnetic disk basically. Okay. So, in magnetic disk the digital data is stored on the disk surface along concentric circle, as you can see over here. A single disk having many such tracks. Okay. So, you can see that a single disk has got many such tracks, and this is divided into the sectors actually. Okay. And the single read write head is used for each disk surface. Large amount of data can be stored on such assemblies of disk as 100 of gigabytes are now common. The disk is divided into sectors, and a hard disk might have about say 2000 tracks per surface and around 32 sectors. Okay. So, this is how it could be. So, we have the disk read and write heads are there. Okay. Arm extend to move heads over the track. Then let us come on the display devices basically. So, the many display systems use light indicators to indicate on off status of or give the alphanumeric displays, okay, that is the alphabet and numbers. So, here as you can see this is the 7 segment display, okay, and there could be a 4-bit binary code input that can be used to generate input to switch on the various segment, okay, that I can explain in the next slide. And we could also have another format where we could have a 7 by 5 dot matrix. Okay. So, we have 1 to 7 rows here and 1 to 5 column here, and by lighting the different elements in this one we can generate the alphanumeric characters. So, if we look at the 4-bit binary code input for that. So, suppose the binary input is 0000, okay. So, this we could get by segment activation of, that is all the segments except the middle one, okay, that is G is 0, as we can see this is the G, okay. So, except the middle one, this is there, we get a 0 number. Okay. Similarly, for binary input 0001, okay, what we get basically is 2 to the power 0, which is 1, and this 1 we can get if my B and C are lightened. Okay. So, B and C are lightened means that basically this one and this one is lightened, I can get the 1. Okay. So, like this way we can get the 7 segment display. Okay. So, for different type of binary inputs, okay, the different segments can be activated in order to get the different numbers being displayed. The light indicators for each display might be neon lamp or LEDs, that is light emitting diodes, or the liquid crystal displays, which we call it as the LCDs. Okay. Now, let us look at the light emitting diode. I have discussed this thing in during my introductory classes, okay, in the first week. So, you can refer it over there also. So, these LEDs are cheap and require low voltage and low currents. Here you can see the basic form of LED basically where reflectors are used to direct the light emitted. Okay. You can see the reflector over here, and this is the LED chip, and they reflect the light. Okay. A standard resistor of 150 ohm is used in series, and these LEDs are available as a single light display, 7 and 16 segment alphanumeric display in dot matrix format and in the bar graph form. So, here we can show the common anode connection arrangement of the 7 LEDs, as you can see over here, okay, to give 7 segments of a display of the form which I have shown previously, and inputs are elements are going active by input going low, and then we can have the other arrangement where elements are going active by input going high. Okay. So, this way. Often the output from the driver is not in the normal binary form, but in case in the BCD form, that is the binary coded decimal form. Okay. So, input to encoder. Okay. So, the driver output has then to be decoded into the required format for the display. Okay. So, the 7447 is a commonly used decoder for driving display, as you can see over here. So, you have the BCD input and you can have the 7447 the decoder to display, and this is 220 array ohm array, and then you have the display. Then dot matrix display, the basic form used for a 5 by 7 dot matrix LED display is shown over here. So, here you can see 1, 2, 3, 4, 5, there are 5 columns and you have the 7 rows over here. Okay. And the connections are in such a way to turn a particular LED, power is applied to its column and its row is grounded. Okay. So, that is how it is done, and this display enables all the ASCII character to be produced. Then the liquid crystal displays or the LCDs, it has no light of their own, but rely on reflected light or the transmitted light. Okay. The material is compounded with long rod shaped molecules, which is sandwiched between the two sheets of polymer containing microscopic grooves. Actually, the arrangement of polymer sheets and the molecules are here, as you can see over here. Okay. So, that is there, and molecules aligns as the light transmits or not. Okay. So, that is there. Have different segment display as the LEDs, and an AC electric field of about 3 to 12 volt is used to turn on any segment. Okay. So, here as you can see that direction of polarized light, and this is how the light is being direction of polarizer. So, light is getting transmitted over here. Okay. And here when the voltage is applied, these molecules gets aligned basically, and you do not get the light transmitted. Now, let us look at the data acquisition system. Okay. The data acquisition system is basically used these days to get the input data basically. Okay. So, this tend to be frequently used as a system as a system as analog to digital converter, processing, analysis, digital to analog converter to display by the computer. Okay. So, there are computer with plug-in boards, the basic elements of the DOQ board and the DOQ system using plug-in board with a computer for the hardware is like this. You have connection to computer bus. Okay. PC bus interface is there. So, you have the digital input output, analog output, and analog input ports are over here. Okay. So, you have the inputs from say sensor, there is signal conditioning, and then you can put it in the computer board. Data loggers are basically this is the term used in the DAQ system, which allow it to work away from the computer, as computer send the program will store in memory card or inserted in the logger basically. So, as you can see that you have the digital input. So, digital multiplexer is used to select the proper input. You may have the analog input also for example say the thermocouple input. Okay. So, that is there. So, analog multiplexers are there, and if you have the analog signals, then amplifier has to be used and analog to digital converter has to be used. Okay. So, sample digital signal is there, your sample analog signal which has been converted into the digital signal, that is there. Okay. And then you can have these things going to the microprocessor, okay, where you have the program unit, and you can have a remote control of this microprocessor. Okay. And from here you can have the control signal for the multiplexer. Okay. And here from the microprocessor you could have connection for display, printer, floppy disk and the other systems. So, these are the references. If you want to read further, okay, you can refer these books, specifically the Bolton Mechatronics. Thank you. Good morning to you all. I welcome you in this lecture on mechatronics. Today we are going to talk about the signal conditioning and use of op-amp as a signal conditioner. This block diagram essentially shows the important mechatronics components, okay, where you can see that usually we have an say actuator, okay, and there is a sensor, all right, and you have input signal conditioning and interfacing. Then you have the digital control architecture and output signal conditioning and interfacing, okay, and then we have a display for viewing purpose. Here as we have been discussing today, out of these mechatronics components, I am going to talk about the input signal conditioning and interfacing. Okay. So, how the sensor signals can be interfaced to your microcontroller. Okay. So, let us look at what are the basic requirement for the signal conditioning. Okay. So, the signal conditioning is needed because whatever signal we get from the sensor, this signal may be too small to be amplified, okay, or they may have certain interferences which need to be removed. Many times this signal could be a non-linear signal, and we may require a linearization process through linearization of the signal through some means, or the signal could be an analog signal, okay, and we know that the microcontroller they take only digital signal. So, we need to convert this analog signal and make it as a digital signal, or if your signal is digital, say you are getting from the microprocessor a digital signal, you may require it to be made to the analog signal, so that you can feed it to the actuator. Okay. Sometimes the signal could be, say, a resistance change, and we want to convert it into a, say, current change signal, okay, or your signal could be a voltage change signal, and we want to make it a current change signal. So, these may be the varieties of requirements for which we need to have the signal conditioning. Then, as I said, the signals has to be sent to the microprocessor for the processing purpose. Now, we need to send these signal to the microprocessor from the sensor. We need to interface it. We require certain type of interfacing of the sensor signal with the microprocessor. Okay. What could be the simplest interface? As all of you know, it should be a piece of wire where we can just connect your signal output port to the microprocessor input port. Okay. So, simplest interface could be a piece of wire. Okay. And these interfaces, when we are going to do for the signal conditioning and protection, signal conditioning purpose, there has to be certain protection also, so that your abnormal signals are not able to damage your microprocessor. Okay. For example, these microprocessor need to be protected against excessive voltage or signal of, say, wrong polarity if by mistake it comes. So, there should be safety provisions in the interfacing to take care of these wrong polarity. And microprocessor requires, as I said, input to be a digital one. So, if your sensor output is analog, say a potentiometer giving you an analog voltage, then you require this analog signal to be converted into a digital signal. Okay. And we may require analog signal to be amplified before being converted into a digital signal. So, all these type of tasks could be done in the unit what we call it as the interfacing. Okay. In the interfacing unit, we can do all these tasks. There are certain more requirement. Even many times digital signal need to be conditioned for better quality, means if we do not have a better quality digital signal, we may require it to be better condition it. Okay. And actuator might require analog signal. The digital output from microprocessor needs to be converted into the analog signal. For example, if you take case of a say DC motor control. Okay. So, you need to give the DC motor an analog signal. Okay. The digital signal and the signal coming out from the microprocessor, they are digital in nature. So, we need the conversion from digital to analog. Okay. Protection for any signal being inputted back to the microprocessor is also required. So, these are the things which are taken care by the interfacing units. Okay. Now, signal conditioning process may occur or the following process may occur during the signal conditioning. Okay. As I said, protection to prevent damage to the next element. Okay. That is a microprocessor as a result of high voltage or current, it may get damaged. Okay. We need to have a protection unit. Okay. And this could be a series current limiting resistor, or normal fuses to break, okay, so that the fuse breaks and it protects your microprocessor, or polarity protection could be there, or the voltage limiting circuit. So, all these are the provisions which could be there. And getting the signal to be right type of signal, okay, making the signal into a DC voltage or current, okay. So, there could be various example. For example, if we are looking for getting a right type of signal, so if you look at a Wheatstone bridge, okay, there what is happening basically, there we have having the change in resistance, resistance change in the strain gauge, and that is converted into voltage change, okay, by the Wheatstone bridge and out of balance voltage, okay, and making signal digital or analog as the case may be. Then getting the right level of signal, as I said, say the thermocouple signals are very minute in the range of say millivolt. Okay. So, we need this signal to be amplified, okay, and say as we are going to talk in the coming slides about the operational amplifiers. These operational amplifiers are widely used for the amplifying purpose of these signals, okay, and then we may need to eliminate or reduce the noise by using various filters, okay. I will also be talking about filters maybe in the next lecture. Then as I said, we may need to manipulate the signal, okay, that is making it linear of some variable, okay. For example, the flow meter signal, okay, is a non-linear, and so the signal conditioner is used to make it as a linear signal. Okay. Now, after all this, let us look at operational amplifier, which is a very popular element, okay, very popular device, and it is widely used for many of the signal conditioning operations. Okay. So, first we will be looking at the basic characteristic basic model of the operational amplifiers, okay, and in next lecture I will be talking about the use of operational amplifiers as the signal conditioner, okay. So, these operational amplifiers, in short, these are called as op-amps, okay. It is basically high gain DC voltage amplifier, okay, and they have got a differential input and usually a single ended output, okay. So, this is there, and the gain of these amplifiers is of order of 100,000, very high gain, okay, and ideally it increases the amplitude of a signal without affecting the phase relationship, okay, of different component of the signal. So, that is another beauty of it, okay, and how it is available in the market. It is supplied as a IC or integrated circuit on a silicon chip, and it is packaged in 8-pin dual inline package integrated circuit chip, okay. So, the op-amp is available in the packaging, as I said. 741 op-amp is very widely used operational amplifier, okay, and then you may ask, what does it consist of, okay. So, the internal design of the commercially available 741 IC consists of what else? Transistors, okay, resistor and capacitor. So, these three components put in a combination basically constitutes the 741 op-amp, okay. that is there, and these op-amps can be combined with external discrete circuit component to create a wide variety of signal processing units, signal processing circuits, as I said. External discrete components here, the one which I am talking about here are basically you could have the resistances, you could have the capacitors, okay, which are external to op-amp circuit, and by putting them in the different combinations you can get the different type of the signal conditioning, okay. That is there, and it is a building block for more complex electronic circuit like say inverting amplifier, the one which is used to invert a signal as well as amplify it, non-inverting amplifier, okay, that is just amplifying the signal, summing amplifier, that is summing of the two signals, okay, then integrating amplifier, that is the signal being integrated, differential amplifier, that is the signal being differentiated, logarithmic amplifier, okay, then comparator, analog to digital and digital to analog converter, active filters, okay, I will be talking about all this, and the sample and hold devices. So, all these are the possible use of the op-amp. So, this is how it looks like basically, as I said, dual pins are there. So, you have the two lines of the pins basically. So, you have say here 1, 2, 3 and this is 4, 5, 6, 7, 8. So, there are 8 pins in it, and this is packaging and pin numbering of 741 op-amp amplifier, and basically there is a mark here just to identify that from left hand side of that you have to start counting the pins, okay. So, this is how this is, and so this is how the packaging consists of, and the pin description of these 8 pins is basically, one is offset null, the second is inverting input, that is there, third is the non-inverting input, then you have the 4 is the negative voltage supply, usually minus 15 volt, then 5th is the offset null, 6 is the output voltage from where the output is taken, and 7 is the positive voltage supply, that is 15 volt, and 8 is the offset null. So, inside whatever you are seeing, so this is the actually how these op-amp are described. So, the terminals which are usually shown here, usually shown for the op-amp are the inverting input, non-inverting input and output. Okay. So, that is why you can see the, these connections over here, and many times we also show the voltage supplies terminals. So, here you can see that the negative voltage supply and the positive voltage supply. Okay. And as I said, you may be eager to see how does the op-amp internal design looks like. So, you can see here there are various transistors are there, resistors are there, okay, and you can see the various ports, that is offset null, that is 1 here, then we have the second is inverting input. So, this is inverting input, third is non-inverting input, then fourth is the power supply, you can see this is the fourth is the power supply, fifth is the offset null. So, you have the offset null, 6 is the output and so on, okay. 7 is the again positive power supply. So, this way it is there, and inside you have the transistors, resistors being connected. And if you go to the market to buy this op-amp, this is how these are available. So, you will find out this 741 being imprinted over there, and this is how the 741 you will be seeing. Okay. So, this is how these are commercially available form of the 741 op-amp. Now, let us look at and try to understand the model of the amplifier. Okay. So, generally an amplifier is modeled as a two-port device with the input and the output voltage reference to the ground. So, this is how the amplifier is modeled basically. So, you have a input side here and you have the output side. Okay, and input and output voltages are reference to the ground over here. This is the input current, output current, input voltage and output voltage. Okay, and as you know these are the amplifiers. So, there is going to be gain in the voltage, and this gain is represented by say a letter mu, and this is output by input, V out by V in. The input impedance is defined as V in by I in, that is the input impedance, and most of these amplifiers are designed to have very large input impedance, so that very little current is drawn from the input. Okay. So, as I will be talking about, this is one of the very important assumption which we also take in the modeling of these operational amplifiers. Okay. So, the output impedance of amplifier is basically Z out is V out by I out, and it is a measure of how much the output voltage drops with the output current. Here the output drop voltage drop is measured relative to the output voltage with no current. Okay. So, this is how it is done, and most amplifiers are designed to have very small output impedance, so that the output voltage will not change much as the output current changes. Now, let us look at the ideal model of the amplifier, operational amplifier. So, as I was saying, so this is the way it is represented basically. So, you have the inverting input terminal here, and you have the non-inverting input terminal, and you have the output terminal over here. So, this is how the symbolically the op-amp represented. Okay. And an ideal op-amp is a differential input, okay, single output amplifier. So, as you can see that there is a differential input and single output is there amplifier, and this has got an infinite gain actually. Okay. And voltages are referred to the common ground, and as I said, it is an active device. Okay. It require connection to an external power supply, as I have talked about it. It is usually plus 15 volt and minus 15 volt. And since op-amp is an active device, output voltages and currents can be larger than the value applied to inverting and non-inverting terminal, okay, because it is an active device, we are supplying power to it. Okay. And an op-amp circuit usually have a feedback. Okay. So, from the output side you have connection to towards the input side, that is what we call it as a feedback. So, the op-amp circuit usually has feedback from the output to the inverting input, and this feedback results in stabilization of the amplifier and helps in the control of the gain, as we will be looking in the subsequent slides as well as in lecture. Okay. Now, let us look at the equivalent circuit of the op-amp. Okay. So, with this assumption, whatever assumptions we have taken, with these assumptions here, these assumptions here, we can draw the equivalent circuit. Okay. So, in the equivalent circuit you can see here we have the two voltage sources source V1 and V2 over here. So, this is the input voltage and you have the output voltage over here. This Vin is the input input voltage. This although we have assumed yes, we have assumed that input side is going to have high input impedance. Okay. It has infinite impedance at both the inputs. Okay. Hence, no current is drawn from the input circuit. Okay. So, therefore, the I2 is equal to I1 is equal to 0 over here. Okay. And it has infinite gain. Okay. So, infinite gains mean mu is equal to V out is equal to V in. So, where what is V in? V in is basically V2 minus V1 from here. So, infinite gain means that the V in is going to be 0. Okay, and V in 0 means what? You have V2 is equal to V1. Okay, and what does this mean? This means that there is a shorting over here. Okay, this is denoted by shorting of the two inputs, and usually some small resistance will be existing over here. And it has 0 output impedance. Okay. Again one of the assumptions over here. Therefore, the output voltage does not depend on the output current. Okay. And op-amp may draw current up to a limit depending on its power handling capacity. Okay. So, that is there, and here in this figure you can see that this is the mu V in where mu is the gain of the amplifier. Then let us look at the inverting amplifier. Okay. That is the one which inverts the input signal. Okay. So, in case of inverting amplifier, it inverts the input voltage. Okay. So, here to achieve this, two external resistances are connected to the op-amp. Okay. So, whatever op-amp circuit we have seen, we are using two external resistances. One is R1 at the input side, okay, of the inverting terminal, and other is the RF, that is the feedback resistance in the feedback path. Okay. So, these two are the external resistances which I talked to you. These are the two external resistances which we are using in order to invert the voltage signal. Okay, invert and amplify the voltage signal. So, let us look at the equivalent circuit for an inverting amplifier. Okay. So, here as we assumed that this is short end over here. Okay. So, we shorted it here. Signal is provided from non-inverting inverting terminal, and the non-inverting terminal is earth, grounded basically. Okay. So, this is the ideal model. You have some load over here, you get the output voltage over here. Okay. And this is the output current which is supplied through the feedback. Okay. And you have the input current over here. Now, let us take a point say C over here. Now, if I apply the Clipchamp current law at this point, then what I get? Current in plus this current and this current, both are being coming to to this junction. Okay. So, I in plus I out is equal to 0, no current can flow to the input of the op-amp. Okay. So, that is why we are taking this as 0. So, from this I get I in is equal to minus of I output. Okay. And also the Vc at this point the voltage is 0 because the two input are short at C over here. So, the voltage across this one R1 is going to be what? V1 this side, Vc this side. So, V1 minus Vc is equal to I in R1, and since this Vc is 0, V1 is equal to I in R1. So, because this is 0 over here. Now, let us look at the voltage across this feedback resistor, okay, RF. So, I have V out and I have Vc. So, V out minus Vc is equal to I out RF over here. Again Vc we take it as 0. So, V out is I out RF since Vc is 0. So, V out is I out we have already found out in the previous slide is equal to minus of I in. So, I put this V out is equal to minus I in RF. Okay. And we have already seen that V1 is equal to I in R1. So, if I divide this is what I get. So, here what we have got? V out, basically we have got V out is equal to minus a factor RF by R1 into V1, and V1 is the input signal which I have supplied through the inverting terminal. Okay. And so, depending on what value of RF and R1 I am taking, I am going to get a gain of it. Okay. I am going to multiply this with this V1. So, my V1 signal is going to be amplified by this particular ratio RF by R1, and this RF and R1 it is dependent on me because these are the external elements which I have put into the op-amp circuit. Okay. So, what we have done basically, so this was my input signal basically. So, here since there is a negative sign, it means that the signal is getting inverted, and if your RF is more than R1, then you are getting the signal amplified also. So, this is how you are going to get it. So, this is there is inversion from here this is positive, but here this is negative, as well as you can see the amplitude also being increased. Okay. So, this is what is actually the inverting of the signal. Now, let us see the non-inverting amplifier. Okay. So, in case of non-inverting amplifier, what we do is that we supply the signal through the non-inverting terminal over here. Okay. And this RF is already there and this R1 is already there, and this end is that is inverting terminal end is connected to the ground. Okay. So, as the name indicates, non-inverting amplifier amplifies the signal without inverting it. Okay. And here the input is applied to the non-inverting input, and a portion of output is also fed back to the input. Now, let us look at equivalent circuit in order to analyze this thing. Okay. So, if we look at the equivalent circuit over here, so again this is my input voltage, this I have grounded. So, this is 0, this is my input current, this is my output current. Okay. And these two terminals are shortened with the assumption which we have taken. Okay. So, the output voltage at node C over here, this is going to be V2 because this side is 0. So, Ohm's law, if we apply across the resistor, so this is 0 minus V2 by R1. So, this is I in is minus V2 by R1, and similarly at RF if I do, so V out minus Vc V out minus V c is equal to I out into R f. So, and what is here, this V c is basically you are going to get the V 2 over here this side. So, I out V out minus V 2 by R f. So, from this equation I get V out is equal to R f out plus V 2, and Kirchhoff current law at C basically will be giving me I in is equal to minus I out, and so I have V 2 is equal to R 1 I out. So, from here V 2 is equal to V 2 is equal to R 1 I in. So, I in is minus I out. So, I put it over here R 1 I out, and V out is equal to V 2 plus R f I out. So, here let us divide this equation by V 2. So, V out by V 2 is equal to 1 plus R f I out by V 2, or V out by V 2 is equal to 1 plus, and what this is basically from here we get I out is equal to V 2 by R 1. Okay. So, if I substitute here I out is equal to V 2 by R 1. So, V 2 get cancelled. So, I get R f by R 1. So, here you see what we have, my output signal is equal to 1 plus R f by R 1 times V 2. So, this was my input signal, okay, and here this is the factor which amplifies my signal. Okay. So, the non-inverting amplifier has a positive gain more than or equal to 1, because you have addition by 1. So, you have more than or equal to 1, that is there. Then we have buffer or follower. This is again a very important important modification or important use of the op-amp basically. Okay. So, here what is done is that your output is shortened to the inverting input terminal over here, as you can see in this figure. So, this is shortened basically, this feedback this is directly connected to this one, okay, that is the inverting terminal. So, for non-inverting amplifier we have seen V out is equal to 1 plus R f by R 1, okay, the previous one which we have devised this one, okay. So, V out by V 2 is equal to 1 plus R f by R 1, okay. So, if we take here this R f is equal to 0, okay, that is whatever we had. If I remove that and say R 1, if I take very high input impedance, then we get what? V out is equal to V 2, okay, or the output voltage is equal to the input voltage, okay, and here the high input impedance isolates the source from the rest of the circuit, okay, and this is what is called as a buffer. Then in the amplifiers actually there is some error, what we call it as the offset voltage. Ideally, if two inputs are shorted, there should not be output, okay, but actually some output is there, okay. So, to compensate this, apply suitable voltage between the two terminals, and this is what we call it as the offset voltage, and this is how the offset voltage correction is provided. And we talked about the ideal op-amp and its characteristic, we draw the equivalent circuit of it, but now let us look at how the real op-amp looks like, okay, and what are the characteristic of the real op-amp, okay. So, the actual output deviates its characteristic from the ideal op-amp, as I said, okay, and real op-amp has very high input impedance impedance. So, little current is drawn at its input. Yes, ideal open we said that it has infinite input impedance, but you do not have exact infinite value, but you have a very high value, and there is little voltage drop, voltage difference between input terminals, that is also there. Important terminal characteristic of the real op-amp are input impedance and maximum output voltage. Two other important characteristics of real op-amp are associated with its response to the square wave input. How does the op-amp responds to a square wave? Okay, based on that, the two other important characteristics of the real op-amp are defined. Okay. So, when we apply a square wave input to an amplifier circuit, the output is not square actually. Okay. It exhibits a ramp from one level to the next. Okay. And in order to quantify the op-amp step response, which we get basically with the help of the square wave, two parameters are specified. These are the slew rate and the rise time. Okay. So, this is how the slew rate is defined basically. So, this is the input, the red color is actually indicating the input and the blue color is indicating the output. Okay. So, you can see that the output is not same as that of the input. Okay. So, this is your output. Okay. So, how much is the how much time this deviation is at, in how much time it is going to peak in take this input voltage, and what is this del V. Okay. So, the slew rate is basically defined by this delta V divided by delta T. Okay. And it is the maximum time rate of change possible for the output voltage. Okay. And the other parameter, as I said, it is rise time, and it is time required for the output to grow from 10% to 90% of its final value. Okay. And it is specified by manufacturer for a specific load and input parameters. Okay. And frequency response is an important characteristic of real op-amp. Ideal op-amp exhibits infinite bandwidth. Okay. So, we say that it is suited for any frequency range, but actually it is not so. A real op-amp has a finite bandwidth, which is a function of the gain established by the external components, whatever external components we are going to use along with the op-amp. So, to quantify the dependence of bandwidth on gain, another definition what we call it as the gain bandwidth product that is used, and the gain bandwidth product of op-amp is actually the open loop gain into the bandwidth at that particular gain. Okay. So, this is the typical characteristic, typical op-amp characteristic if we plot frequency versus open loop voltage gain. So, this is the curve which you are going to get op-amp and closed loop response. This is what we are going to get. Okay. So, the typical op-amp exhibits a linear log-log relationship between the open loop gain and the frequency, with the op-amp gain decreases with the input signal frequency. So, you can see that as the signal frequency increases, this gain decreases, and higher quality op-amp have larger GBPs. Okay. The open loop gain is characteristic of the op-amp without feedback. Okay. While the closed loop gain is the overall gain of the op-amp circuit, that is with the feedback. Okay. Here you can see that the closed loop gain is always limited by the open loop gain of the op-amp. Okay. The frequency where the open loop gain curve first start to limit the closed loop gain is what is called as the fall off frequency. Okay. So, this is the frequency where that open loop gain curve starts to limit the closed loop gain. Okay. And as you increase the gain of a circuit, you limit its bandwidth basically, as you can see in this particular figure. Okay. Similarly, if you want a small bandwidth, larger gains can be used. Okay. So, if your bandwidth is small, okay, you are going to be in this region, naturally your voltage gain is going to be more. So, these are the references which you can look into for further reading, and these are the references which I have used to prepare this lecture for you. Good luck. Thank you. I welcome you all in this NPTEL online certification course on mechatronics. Today we are going to talk about op-amp as a signal conditioner. In the last slide, last lecture, I discussed with you the op-amp, its assumptions in the modeling of the op-amp we have seen, and we have seen the use of or how can we use the op-amp to amplify a signal with the help of external elements or external resistors rather. Today in this lecture, we will talk about how can we manipulate a signal. Manipulation, I mean that how can we add the signal, how can we subtract the signal, how can we integrate the signal, how can we differentiate the signal. So, all these and the various other uses of operational amplifier as a signal conditioning unit we are going to discuss today. I hope you will enjoy this lecture. So, here we are at this place right now, input signal conditioning and interfacing. First of all, let us look at the adder circuit. Okay, that is, I have got two signals and I want to add those signals. Okay. So, here what we do, the non-inverting side we ground it. In the inverting side we have the two signals V1 and V2 over here, and these are the input side resistances R1 and R2, and you have the feedback resistance over here. Okay. So, a portion of the output is fed back to the inverting side over here. Now, to see its use at op-amp as the adder of the two signals. Let us analyze it. So, for that purpose I have drawn the equivalent circuit of an adder. Okay. So, these are V1 V2 R1 R2, this is current say through this one I1 I2, and this is output current from over here, and say this is what we are shorting as per the assumptions for the op-amp. Okay. So, now at C we see that if I apply the Kirchhoff current law, I have these three currents coming over here. So, I can just them sum it to the 0, and then I can substitute I1 is simply V1 by R1, I2 is V2 by R2, and I out is V out by RF is equal to 0. So, from here I can just write V out is equal to minus of RF by R1 V1 plus RF by R2 V2 over here. Now, if I take this R1 and R2, they are to be equal to same R. Okay, R1 and R2 as say same equal to RF. Okay. Then if I put it over here, then you can just see that what I get is minus of V1 plus V2. So, sorry. So, I am able to sum up these two signals, and although I am getting this signal inverted, so I can use another op-amp to correct this inversion. Okay. But I am able to get the summation of the two signal over here. Now, let us look at use of op-amp for the subtraction of the two signal. Okay. So, for the subtraction of the two signal in the previous circuit we make some modification over here. Okay. So, at the non-inverting terminal I supply the another signal V2 over here, and there is another resistance of the value RF which is being used over here. So, in this configuration I can use for the subtracting purpose, that is I will be getting V1 minus V2 from this one. Let us see how this is done. So, again I have put up the equivalent circuit for that. Okay. And so, this portion actually I can analyze by over here, as you can see. You have R1, you have RF, this is the point C over here, okay, and this is the V2 over here. I will come back to it little later. Okay. So, the voltage at C here Vc, as you can see, this is basically V2 minus IR1 basically. Okay, because it is V2 minus Vc, this is basically what I into R1. So, you have Vc is equal to V2 minus I R1 over here. Okay. So, from here you see that Vc is equal to V2 minus I can write as V2 by R1 by RF, R1 plus RF into R1. How can I write this I is equal to this one? Basically you can see this equivalent circuit over here. If there is a current I from here, then your V2 is equal to basically I into R1 plus RF. Okay. So, I is actually V2 by R1 plus RF. So, I have just substituted that I is equal to V2 by R1 plus RF into R1. So, that is there. So, from here this is there. Moreover, this Vc or if I simplify this, then what is this V2? Vc is equal to V2, you have R1 plus RF minus R1. So, R1 gets cancelled. So, you have RF upon R1 plus RF. Okay. So, I have this equation the voltage at C. Also as we have been seeing I1 plus I out over here this is going to be 0. So, I1 is equal to minus I out. Now, I substitute for I1 basically, that is V1 minus Vc by R1, and I out as V out minus Vc by RF with a minus sign. So, this is our equation. So, from here I can find out V out Okay, V out I can find out RF by R1, V1 plus VC over here. So, this I out is minus RF by R1 V1. I just simplify this, and the VC I have already calculated in the previous slide over here. Here this one, so I substitute it over here. So, I get this one. So, if I substitute this VC over here, this is what I am going to get. So, here you can see that what I am having is, I am having the difference of these two signals V2 minus V1, and this RF and R1 will basically decide how much I am going to amplify it. Next, let us see the use of operational amplifier as an integrator. So, for that purpose, in the feedback circuit, if I replace the feedback resistor with a capacitor of say capacitance CF, okay, here, and I have a signal say V1 supplied to the inverting side, and the non-inverting side is grounded over here. Okay. So, the voltage across capacitor is actually Q by C. This is the general equation which we all know. Okay. So, from this one I can write about V out, if I differentiate this, then V out by dt is basically going to be 1 by Cf dq by dt. Okay. So, V out by dt is 1 by Cf dq by dt, or this one dq by dt, you know, this is basically I out. So, I replace with I out, and this is what I have. So, from here I have the V out is equal to integration of I out, I use a dummy variable tau over here, integrate it from 0 to t, and 1 by Cf is there. Okay. And you see I1 plus I out is equal to 0, again from the assumption for the op amp. So, I out is minus of I1. Okay. And this I1 is actually from here V1 by R1. So, what I get basically here is V out is equal to this one minus 1 by Cf R1 V1 dt, because this I out is minus what I1, and this minus I1 will be basically minus V1 by R1. Okay. So, this is what I get, and here you see what we have got is that my input signal, that is which was V1 over here, that has been integrated. Okay, and this is what I am getting output. Okay. So, this way I can use the op amp as an integrator. Next, let us see the op amp as a differentiator. Okay. So, we can get the differentiator circuit if we replace the input resistor of the inverting op amp circuit by a capacitor as seen in this figure. Rest of the things are same, that is you have a feedback path here with the feedback resistance RF, and this non-inverting side is grounded. So, if I look at the equivalent circuit over here, say this I1 is the current at the input side, I out is the current at the output side. Okay. So, dV1 by dt basically can be written as I1 by C1. Okay. So, we can write this one, and we see I1 is equal to minus I out. We already know from our earlier assumption for the op amp. So, my I out is basically V out by RF, which we can derive from over here. So, V out is minus RF I1 I can write after substituting for this one. So, my V out is equal to RF minus RF, and I1 I can replace this from here. Okay. So, that is C1 dV1 by dt. So, here you can see that what we are getting is basically my this input signal is getting differentiated, and it is multiplied by some factor with a inverting sign over here, and that I am getting the output. Okay. So, this is what this is how we get the differentiated signal. Then coming to the other uses of the op-amps, these are used very popularly for the as a sample and hold devices, and sampling and holding is basically required when we are talking about the conversion of analog signal to the digital signal. Okay. So, in this when we are talking about conversion from analog to digital, okay, signal value must be established while it is converted to the digital representation. Okay. So, here what is done is that here this is output is connected to the inverting side over here, and there is a switch which is used, and there is a capacitor with capacitance CH that basically which is used for holding of the holding purpose, and this is your input side. Okay. So, when this switch is closed, when this switch is closed, basically that time it is used as a buffer. Okay. So, whatever output you are getting, that is going to be the same as the input. So, V out is equal to V 2. Okay. And when the switch is opened, this switch is opened over here, then the capacitor, this CH actually holds the input voltage corresponding to what? Last sampled value, since negligible current is drawn by the follower. Okay. So, the relationship will be what? This V 2 at the t sample time, this is going to be there, V out, that is t minus t sampled. Okay. So, this is what is going to be there, where t sampled is the time when the switch was last opened. And this sample and hold amplifier are used to hold an instantaneous value of the analog voltage until an AD converter is ready to convert the signal. Next, purpose of or good use of the op-amp is as a comparator. Okay. So, as the name indicates, the comparator basically compares the two voltage signal. Okay. It shows which of the two signal is larger. Okay. So, for that purpose what we do is that we in the inverting terminal we send one signal, say V1, and in the non-inverting terminal we send another signal of voltage, say V2. Okay. So, there is no feedback. Op-amp with no feedback can be used as a comparator. Okay. That is it is in the open loop configuration, since we are not going to have any feedback. Okay. Now so, one of the voltage is applied to the inverting input and the other is applied to the non-inverting, as I explained. Now, here there are three things possible. If V1 is equal to V2 sorry, if V1 is equal to V2, there is no signal. Okay, that is no output is over there. Okay. So, you are basically at this place. Okay. Here I have plotted input versus the output, and if V1 is greater than V2, okay, then output jumps to say a minus 10 volt range over here. Okay. There is saturation over here. So, this comes to the minus 10 volt. Alright, and if V2 is greater than V1, it jumps over here, other side. Okay, jumps to plus 10 volt. So, comparators can be used to determine when a voltage exceeds a certain level, that is the output then being used to this output then can be used to initiate some action in your subsequent circuit. One of the very beautiful application of the this is in the CD player, to check the focus of the laser light on the CD. Okay, so you have the op-amp over here. There are two terminals V1, V2, and this is your output side. Okay, so these terminals are connected to the photodiodes over here. Okay, these photodiodes are there, and this one say this V1 side, this inverting side is connected to this one and this one, whereas the non-inverting side is connected to this diagonally this one. Okay, this one, and here say they are connected to this one. Alright. Now, when there is a laser beam in perfect focus, there is same voltage, okay, same voltage. So, V1 is equal to V2, you get it from here. Alright. So, you do not have any signal. Okay. And when there is out of focus, either this way or it is this way, you have a certain signal. Okay. So, if you have the beam out of focus, then you have a signal. So, this is the application where the comparator is used. Now, let us look at the filters basically. Okay. Filters are also important device in a mechatronic system for the signal conditioning purposes. Okay. It is as the name indicates, it is a process of removing a certain band of frequencies from a signal and permitting other to be transmitted. Okay. And these filters could be either active or passive. Passive, as the name indicates, a filter made up of using resistor, capacitor, inductor, and there is no power source over here. Whereas, the active filters are those which involves operational amplifier, and you know that the operational amplifier need power supply for them to work. Okay, that is why they are called active filters. Okay. So, here you have the example for the passive filter. You have a resistor, capacitor over here, this is your input side, this is your output side, and here you have the active filter where an op-amp is there. Okay. You have resistor, capacitor and all. So, let us look at the definition of these filters basically. Okay. So, low pass filters. Okay. Low pass filter, as the name indicates, they allow the lower frequencies and they block the higher frequencies. Okay. So, this signal transmitted and frequency, if I am plotting, only this range is actually the allowed one. Okay. And other higher ranges are blocked. Okay. And high pass filter, only the higher signal of a frequency higher than a particular frequency, they are allowed. Okay. And others are blocked. Then you have a band pass filter where we allow a frequency of a particular band to be passed through. Okay, that is it blocks all frequency except those within this range. Okay, and band stop filter blocks only the frequencies within a certain range, allowing all other to pass through. So, here this is the pass band, this is the pass band, burst frequency of this range is going to be blocked. So, this is what is the band stop filter. So, the low pass passive filter is this one where you have resistor and capacitor with used in this fashion, and high pass passive filter is this one with capacitor and resistor being used in this fashion. Then let us look at what are the parameters specified in op-amp data sheet. What are the manufacturer, what all parameters the manufacturer specifies in the data sheet for the op-amp. Okay. So, these parameters could be input parameter, output parameter, dynamic parameter, we will look at this. So, the input parameter first of all is the input voltage. Okay. So, it is the maximum input voltage that can be applied between either input and the ground. Okay. So, we have the two input ports, inverting and non-inverting. So, between the either of that and the ground, how much maximum input voltage we can supply. Then the input offset voltage, okay, the voltage that must be applied to one of the input terminal with the other input being at 0 volt to give a 0 output voltage. Okay. So, as I explained in my last lecture about the offset. Okay. So, this is how it is defined. Then input bias current, the average of the current flowing into the both the input when the output voltage is 0. This is what we call it as the input bias current. Then input offset current, it is the difference between the input current when the output voltage is 0. Then input voltage range, this is the range of allowable common mode input voltage where the same voltage is placed in the both the input. Then input resistance, it is the resistance looking into either the input with the other input being grounded. Now, what are the output parameters? These are the output resistance, output circuit current, output voltage swing. What is the output resistance? It is the internal resistance of the op-amp output circuit. And what is the output short circuit current? It is the maximum output current that the op-amp can deliver to a load. And what is the output voltage swing? It is the maximum peak to peak output voltage that the output can supply without saturating or the clipping. Then what are the dynamic parameters? So, dynamic parameters are open loop voltage gain. Okay. So, it is the ratio of the output to the differential input voltage of the op-amp without external feedback, as the name indicates it is a open loop voltage gain. Then what is the large signal voltage gain? It is the ratio of the maximum voltage swing to the change in the input voltage required to drive the output from 0 to a specific voltage. Then what is the slew rate? I talked about slew rate in my previous lecture also. It is the time rate of change of the output voltage assuming a step input, okay, with op-amp circuit having a voltage gain of 1. Then what are the other parameters? There are certain other parameters which are also specified. Maximum supply voltage, it is the maximum positive and negative voltage permitted to power the op-amp. Then what is the supply current? It is the current that the op-amp draws from the power supply. Then common mode rejection ratio, it is the ratio of the difference mode gain, okay, that is the output gain corresponding to the difference between the input, to the common mode gain, that is the output gain when the same voltage is applied to both the inputs, and this is usually expressed in terms of decibels. Then the channel separation. See, when there is more than one op-amp in a single package, a certain amount of crosstalk is present. Okay, and what do you mean by this crosstalk? Okay, that is the signal applied to the input of one op-amp producing a finite amount of signal to the second op-amp, even though there is no direct connection between both the op-amps. Okay. So, this is specified by the channel separation. Okay. So, these are the further references which I have used in preparing these lectures. So, if you want to read it more, please go through these references. Thank you very much. I welcome you all in this NPTEL online certification course on mechatronics. Today we are going to talk about a very important component, analog to digital converters. Many of the sensors which we are using in a mechatronic system, they give the analog output, and the microprocessor or microcontroller which are going to process these signals, they require the digital input. So, is the need of analog to digital converter. Okay. So, in this lecture I am going to talk about this. I hope you will enjoy that. So, here we are at this phase, input signal conditioning and interfacing, and here I am going to talk about this analog to digital converter. So, see how does the analog signal looks like. So, the analog signals are actually continuous signal, and this is how they look like actually. Okay. Whereas, the digital signals are basically they look like this, they are either on or off. Okay. So, most of these digital signals have got only two states, as I said, on and off or high and low. A system using two state signal allows the application of very powerful logic, very powerful tool called Boolean logic and binary number representation. So, I will be talking about these also in my upcoming lectures. So, let us talk a little about the digital signal. As I said, the output from most sensors tends to be analog form, and the size of output being related to the size of input some way or the other. And as I said, a microprocessor is used as a part of measurement or control system, and it can take only the digital signal. Okay. So, these sensor signal need to convert it into the digital form before they can be used by or they can be processed by the microprocessor. Likewise, most actuators operate with analog input. Okay. So, for that we require the conversion from digital to analog, and that I am going to talk in my next lecture, the analog to digital digital to analog conversion. Okay. So, the digital output from microprocessor has to be converted to analog form before it can be used by actuator, as I said, and I am going to talk about this component, that is digital to analog converter, in my next lecture, so that the signal can be used by the actuator. And here as you see, we have the microprocessor. Okay. And I need the signal for microprocessor to be a digital signal. Okay. So, since the most of the sensors are analog sensors, I need one analog to digital converter over here, so that the signal can be processed by the microprocessor. As I said, the beautiful thing with the binary with the digital signal is that we can use the binary or Boolean logic basically, okay, in signal processing. Okay. So, before we proceed, let us have a little about the binary system, so that we have some understanding about it before we proceed further. So, the binary system is based on two symbols or states, that is what we call 0 and 1, and these possibly say 0 may corresponds to a say 0 volt and 1 may corresponds to the 5 volt. Okay. and these 0 and 1 are termed as binary digits or bits. Digit position in a number indicates the weight attached to each digit. In a number, in a binary number, okay, the digit position in number is indicated by how much weight is attached to that. Okay, and weight is increases by a factor 2 as we proceed from right to left. Okay, so this is like this. Say bit 0 is represented by 2 to the power 0, bit 1 is 2 to the power 1, bit 2 is 2 to the power 2, and bit 3 is 2 to the power 3, and so on. Okay. Let us take an example, say number 15. Okay. So, this number 15 can be represented by say or rather I can write 15 as 2 to the power 3 which is nothing but 8, 2 to the power 2 which is 4, and 2 to the power 1 which is 2, and 2 to the power 0 which is 1. So, 8, 4, 12, 13, 14 and 15. So, this gives me the 15. Now, here all these are present. Okay. So, we represent the presence of all these by number 1. So, you have 1 here, 1 here, 1 here, 1 here. So, this is the binary representation of 15, that is 1 1 1 1, and the combination of bit is represents actually the words. So, for 1 1 1 1 is a 4 bit word, and this 4 bit word basically represents a number 15 in the decimal system which as we have seen. So, such a word could be used to represent the size of a signal. Okay. And to have little bigger unit, 1 byte is taken equal to 8 bits. So, this table actually indicates the decimal and their binary equivalents. So, basically as I have just talked about, 1 1 1 is equal to 15, and so in binary if I am writing say 0 0 0 here, that is my all are absent basically. Okay. So, this is actually 0, 0 0 1 is equal to 1. So, actually this is basically what 2 to the power 0. Okay. And this is basically what, this is equal to 2 to the power 1, that is present. So, this is 2, and this is actually what 2 to the power 0 plus 2 to the power 1. So, both these are present. So, this is equal to 3, and here this is basically what 2 to the power 2. So, this is 4, and this is 2 to the power 2 plus 0 plus this is present. So, this is 2 to the power 0. So, you have 5. So, likewise. Okay. So, likewise we can establish a that is we can have a binary representation of a decimal number in a 4 bit representation like this. Now, let us look further on analog and digital signal. Okay. So, analog to digital conversion involves converting analog signal into basically a digital signal, and digital signal we know that it is nothing in the form of binary words basically. So, a clock supplies regular time signal pulses to the analog to digital converter, and every time it receives a pulse it samples the analog signal. Okay. So, this analog to digital converter basically needs a sample and hold circuit basically. okay, for the sampling purpose. Okay. So, you have the input side, you have an analog signal, there is a sample and hold circuit, okay, for sampling and holding of it, and then this is given to analog to digital converter, and you get the output as the digital signal. Okay. So, this is how it is done. So, suppose this is my analog signal, as you can see over here. Okay. So, I have plotted analog signal versus time, and this is my clock signal. So, I am putting my clock at these point as this time basically. Okay. So, at this time if I am clicking my clock, so this value is being picked up over here, okay, and at 0 this value is being picked up, okay, and here this value is being picked up. Likewise, I am picking up the values, okay, and at this time I am putting up a clock. So, this value is being picked up like this. Now, you see, so this is the sampled signal, and if I talk about sample and hold, so this signal is held till the next clock comes basically, okay, next ticking comes. So, this signal is hold up to here, and then at this time interval, okay, another value will be held, okay, and it will be this value basically, okay. So, this value is held up to this duration, and then here it comes to 0. So, the 0 will be held, and then it will be coming over here, the same 0 is held up to here, and until unless this is held. So, this way this signal is being sampled and hold the analog signal. Okay. So, as a result of the sampling, basically we get this one, okay, and this sample and hold unit is necessary because analog to digital conversion requires a finite amount of time, that is conversion time, to convert the analog signal into a digital signal. Okay. So, looking at analog to digital conversion, as I said, analog to digital converter is basically an electronic device that converts analog voltage into a digital code. The output of the A to D converter can be directly interfaced to the digital devices such as microcontroller and computers. Okay. And analog to digital conversion conceptually involves two steps basically, what we call it as the quantizing and coding. Okay. So, that is first you have to quantize the signal, and then you have to give a code to that particular quantized value. Okay. So, the quantizing and the coding, this involves in conversion of analog signal into a digital signal. So, what is quantizing basically? This quantizing is the transformation of a continuous analog input into a set of discrete output states, okay, and coding is the assignment of a digital code for that particular quantized value, okay, word number to each output state. Okay. And the resolution of an analog to digital converter is basically is the number of bits used to digitally approximate the analog value of the input. So, the analog value of input you are being representing by how many bits, that basically tells you the resolution of the analog to digital converter. Okay. So, the number of possible states is equal to the number of bits combination that can be output from the converter. Okay. So, if there is n number of bits, then your number of states are going to be equal to 2 to the power n. Okay. Or say in case of a 3-bit device, it is going to be 2 to the power 3, or that is 8 output states. Okay. And the output states are usually numbered consecutively from 0 to n minus 1. okay, and that is in this case 0 to 7. All right, and total we are going to have 8 states basically. Okay. So, most analog to digital converters use either 8, 10 or 12 bit devices that resolves 2 to the power 8, 2 to the power 10, 2 to the power 12 or 256, 1024 or 4096 states. Then the analog quantization size, this is sometimes called the code width, and this is defined as the full scale range of the AD converter divided by the number of output states. Okay. So, it is V max minus V min divided by n, where n is the number of the output states. It is a measure of the analog change that can be resolved by the converter. Okay. So, the number of analog decision points that occur in the process of quantization is n minus 1, okay, that is 7 in case of 3 bit device. Okay. Consider let us take a 3 bit device which has got 2 to the power 3 or 8 output states as listed. I am going to illustrate that. So, the output states are can be numbered from 0 to n minus 1, and the corresponding code word for each output state is listed as I am going to show in the next slide, and these are going to be the decision points basically, and so the code width will be V max minus V min divided by n, that is 10 minus 0 divided by 8. So, this is around 1.25 volt. Okay. And this means that the amplitude of the digitized signal that has an error of at the most 1.25 volts. Okay. So, the AD converter can only resolve a voltage to within 1.25 volt of the next analog voltage. So, here so, this 10 volt range 0 to 10 divided by 8 basically gives us 1.25. Okay. So, this is 0 to 1.25, 1.25 to 25. So, these are basically we are going to have, okay, and output states are going to be here. This is actually your capital N which I was talking to you 0, 1, 2, 3, 4, 5, 6, 7, 8, and these are the numbers basically means 0 to 1.25 volts, say I am representing by a binary number 0, 0, 0. Okay, and 1.25 to 2.5 volt I am representing by binary number 0, 0, 1. 2.5 to 3.7 volt I am representing by binary number 0, 1, 0. Okay. So, this is how this signal, analog signal is represented by the digital signal. Okay. So, a particular voltage range values are given a particular binary representation after the quantization. So, the question arises that if we are sampling your analog signal, what should be our frequency of sampling, and that criteria has been given by the Shannon. Okay. So, Shannon sampling theorem it basically helps us, or rather gives a guideline that how frequent we should sample our analog signal when we are going to represent it digitally. Okay. So, the first step for analog to digital conversion is to numerically evaluate the signal at discrete instant in time, and this process is what is called as sampling. Okay. And the result is a digitized signal composed of discrete value corresponding to each sample. Now, how fast or how often the signal should be sampled to obtain an accurate representation? Because it is a very important factor, because if yours it needs a high speed hardware and large computer memory naturally, if you are going to do the sampling very often. Okay. So, the Shannon sampling theorem states that the sampling rate of the signal should be more than 2 times, okay, more than 2 times the maximum frequency component in the signal. So, whatever maximum frequency component is there in the signal, you have to sample it more than 2 times of that, okay, in order to retain all frequency components. Okay. So, Fs has to be more than 2 times of the maximum frequency component. Okay. So, where max, or what we is also called as Nyquist frequency, is the highest frequency component in the input analog signal, and the time period between so digital sample we could just evaluate by putting it 1 by Fs. Okay. So, if the sampling rate is actually 5000 hertz, what does this means? This means that the time interval between samples would be 1 by 5000, that is 0.2 millisecond. So, you have to do this sampling of your analog signal at the interval of 0.2 millisecond. Then let us look at a phenomena called aliasing. Okay. If a signal is sampled at less than 2 times its maximum frequency component, then aliasing will occur. Okay. So, say 12 equally spaced samples are taken over say 10 cycles of the original signal. Therefore, the sampling frequency is around 1.2 f0, where f0 is the frequency of the say original sine wave, and because the sampling frequency is greater is not greater than 2 times of f0, it will not capture the frequency in the original signal. Okay. So, the apparent frequency in the sampled signal is 0.2 f0, okay, that is okay, that is going to be there, or the 2 alias signal cycle for 10 original signal cycles it is there. Okay. And because of this undersampling not only result in error, but also create information that is not really there. Okay. So, here you can see in this figure you have the sample points over here, okay, and you have the original signal and you have the alias signal. So, this signal which you have got by sampling, this sampling, this is the alias signal. Then to properly do the analog to digital conversion, okay, that is to properly acquire analog voltage signal for digital processing, the following components must be properly selected and applied in this sequence. So, for example, the sensor is there which gives an analog signal. You need a buffer amplifier in order to amplify that signal. Then you need a low pass filter, okay, so for there, and then you need a sample and hold device, and once you have the sample and hold device, then you need an A to D converter for that, and then of course this can go to the computer memory like this, okay, and this way you can convert this your analog signal into the digital signal like this. So, the buffer amplifier actually isolates the output from the input and provides a signal in a range close to but not exceeding the full input voltage range of the A to D converter, and the low pass filter removes any undesirable high frequency components in the signal that could produce aliasing. Okay, because if you have a high frequency component and if your sampling frequency is less than 2 times of that high frequency component, you are going to get the aliasing. Okay. So, the cutoff frequency of the low pass filter should be no greater than half the sampling rate. The sample and hold amplifier maintains a fixed input value, okay, during the short conversion time of the analog to digital converter, and the converter should have a resolution and analog quantization size approximate to the system and signal. Okay. And the computer must be properly interfaced to the A to D converter system to store and process the data. The A to D system component described can be found packaged in a variety of commercial products called data acquisition, okay, DAC or DAQ cards or module. Okay. And these DAC products are available in a variety of form factors including PC and instrument panel plug-in card, a laptop computer, PC MCIA cards, and standalone external units with standard interfaces, or that is USB. Alright, DAC and modules usually support various high level language interfaces also, that is either C++ or Visual Basic, Fortran, that gives easy access to the product features. So, these are the commercially available product from the National Instrument LabVIEW software. National Instrument are there, and various forms of data acquisition products from the National Instruments, as you can see over here. Now, this analog to digital conversion, what are the methods and how this is done basically. Okay. So, let us try to understand this. The input to ADC is an analog signal and output is binary word, and that represents the level of the input signal we have already seen by quantizing and coding, and this A to D converters are designed based on the different principles, okay, such as successive approximation, flash or parallel encoding, single slope and dual slope integration, switched capacitor, and delta sigma. Okay. So, I am going to talk about the first method, that is the successive approximation. Okay. So, in this case of a successive approximation, basically what is done is that you have a analog input being supplied to a comparator, there is a clock over here and there is a gate, and this gate basically I will be talking about this gate, the details of this gate in my coming lectures. Okay. So, this basically controls the admission of pulses to the storage register, and here is your say 4-bit storage register. Okay. And there is a digital to analog converter, this is being used, and again as I said I will be talking about digital to analog converter in my next lecture. Okay. So, in a analog to digital converter, a digital to analog converter is being used, okay, in this method of successive approximation, and from here we get the digital output. Okay. So, how the process takes place basically, this is illustrated over here, how this conversion from analog to digital takes place. So, a voltage is generated by the by a clock emitting a regular sequence of pulses which are counted in a binary manner, and the resulting binary word is converted into an analog of voltage by digital to analog converter. converter basically. Okay. And this voltage rises in steps and is compared with the analog input voltage from the sensor. And when the clock generated voltage passes the input analog voltage, the pulses from clocks are stopped, okay, being counted by a gate. And the output of the counter at that time is basically the digital representation of the voltage. Okay. And when the comparison could be while the comparison could be accomplished by starting the count at 1, the least significant bit, and the processing bit by bit upwards, a faster method as I said is by this method, that is the successive approximation. Okay. And this involves selecting the most significant bit that is less than the analog value, and then adding successive lesser bits for which the total does not exceeds the analog value. For example, we might start the comparison with say 1 0 0 0, okay, this byte, okay, and that is with these 4 bits. If this is too large, we try with then 0 0 1 0 0, and if this is too small, then we try with 0 1 1 0. So, okay, and if this is too large, we again try with a different number. Now, because each of the bits in the word is tried in sequence with a n bit word, it only takes n step to make the comparison. Okay. So, thus in this successive approximation, basically what is there, you have an analog signal, you sample that analog signal, okay, and give a representation to a digital representation to that analog signal, okay, sampled analog signal, and you check basically and that digital representation is basically converted into an analog for comparison purpose with the actual analog, okay. And when the comparison is there and the deviation is not found, then whatever the digital value has been there, that digital value is actually taken as the analog digital representation of the analog signal. Okay. So, this is how this successive approximation actually works. Okay. I will again explain you. So, you have a clock, you sample it, okay, and after sampling give a digital representation to that, okay, and this digital representation is also available in the form of output. But whether this output has to be taken or not taken, or this is correct or not, to check that, we take this digital signal and use a digital to analog converter and compare it with the analog input. Okay. And we have I have already explained in my previous lecture about the comparator. Okay. So, if where this converted your analog signal and the actual analog signal, if they are comparing, okay, then this particular value of the bit or signal, digital signal is selected or taken as the analog, that is the taken as the digital representation of this analog signal. So, this way you have the digital value of that. Okay. So, if the clock has frequency f, then the time between pulses is naturally going to be 1 by f. So, hence the time taken to generate the word, that is the conversion time, is going to be n times of f, where n is the step to make the comparison. So, these are the further references which you would like to go through for further reading. Thank you very much. I welcome you all in today's NPTEL online certification course on mechatronics. Today we are going to talk about digital to analog converter. Okay, and before that I would like to discuss about representation of any signal as a Fourier series. So, here we are basically that is a digital to analog converter. Okay. So, digital to analog converter is basically used in the output signal conditioning and interfacing. So, as I have been talking to you that the signals which we get from the microprocessor or digital control architecture, these signals are digital in nature, and these signals need to be converted into the analog signal if we want to send or if we want to send those signal to an actuator. Okay. So, here we require the digital to analog converter. So, Fourier series representation of signal, I wanted to have a little discussion on this topic here before I present to you the digital to analog converter. Basically, this gives us some visualization about analog signal and its mathematical representation that is mathematical representation of the analog signal. So, the fundamental premise for the Fourier series representation of a signal is that any periodic waveform can be represented as an infinite series of sine and cosine waveforms of different amplitudes and frequencies. And when this infinite series is summed up, it will reproduce the original periodic waveform exactly. In practice, we do not need the entire infinite series because a finite number of sine and cosine waveforms can adequately represent the original signal. So, the fundamental or the first harmonic frequency omega 0 is defined as the lowest frequency component of a periodic waveform. The other sine and cosine waveforms have frequencies that are integral multiples of the fundamental frequency omega 0. Okay. So, the second harmonic would be represented as 2 omega 0, third harmonic will be represented at 3 omega 0 and so on. The Fourier series representation of an arbitrary periodic waveform ft can be expressed mathematically as this. So, ft is equal to C0 plus sigma n from 1 to infinity a n cos n omega 0 t plus sigma n 1 to infinity b n sin n omega 0 t, okay, where C 0, this is basically you can see that it is a DC component of the signal, okay. Then the two summations here are the infinite series of sine and cosine waveform. Now, here this a n is defined like this, 2 by t 0 to t f t cos n omega 0 t dt, and b n is defined like this as 2 by t 0 to t f t sin n omega 0 t dt, and C 0 is defined as 1 by t integration from 0 to t of f t dt, and this, if you evaluate this, will turn out to be a 0 by 2. Here t is the period of the waveform, okay. Suppose we have a ideal square wave as an example of the periodic waveform, okay. So, I have a ideal square wave whose magnitude is say 1, say between 0 to this is actually t by 2, okay, time, and here you have time t. So, between 0 to t by 2 this is 1, and between t by 2 and t it is minus 1, okay. Here t is the period, okay. So, the square waveform is defined like this. Now, this waveform, if I want to represent okay, mathematically, okay, that is as the using the Fourier series, then we can evaluate the different components here, okay. That is, we can evaluate C 0, we can evaluate A n, and we can evaluate B n. Then we can see that how we can represent this signal, okay. So, a n 0 to 2 by t 0 to t f t cos n omega 0 t dt. So, now I substitute for f t. So, 0 to t by 2 it is 1 basically. So, 1 into this one, and here this is minus 1. So, you have a minus sign over here, okay. And now I take the integration of this. So, sin n omega 0 t by n omega 0 minus this sin n omega 0 t by n omega 0 t 0 t by 2 to t, this is there, and then I substitute, that is I evaluate these integrals, okay. And we know that the fundamental frequency of a square wave is related to period as omega 0 is equal to 2 by t 2 pi by t. So, if I substitute this over here, this is what we get a n is equal to 0, and so also a 0 is equal to 0, because here basically we will be getting sin n pi type of terms. If I am putting omega 0 as 2 pi by t, this is what I am going to get. Then we can similarly find out the coefficient B n as 2 by t 0 to t f t sin n omega 0 to dt. So, this is 0 to t. So, I take 0 to t by 2 and t by 2 to t. So, I multiply with 1 here and 1 minus 1 over here. So, I have a minus sign over here, okay, and then I evaluate this, okay. So, this is what I am going to get, minus cos n omega 0 t by 2 plus 1 plus cos n omega 0 t minus cos n omega 0 t by 2. So, this since we have omega 0 is equal to 2 by 2 pi by t, I can substitute it over here and evaluate these terms basically, okay. So, this is what I am going to get, okay. And you see cos n pi is equal to minus 1, and if n is odd, so I can evaluate B n as 4 by n pi, and if n is even, B n is equal to 0. Okay. So, this I can do. So, the Fourier series representation of a square wave of amplitude 1 is given by this one. So, this is our original equation. C0 we have evaluated as 0, A1 this is 0, C0 we have seen this is 0. Okay. So, here basically we will be getting only odd terms, because even terms we have seen that in case of even terms Bn is equal to 0. So, this is what I am going to get B1, B3 and B5, okay. And then I can substitute for these 4 by pi here, 4 by 3 pi, 4 by 5 pi and so on, and using an infinite sum I can represent this as 4 by, here you have the odd term. So, 2n minus 1 times pi and sine, here again you have the odd term. So, 2n minus 1 omega 0 t. Okay. So, this is how my Ft is basically represented over here. Okay. So, this is the Fourier series representation of the square wave signal of the unit amplitude. Okay. So, now if you look at the individual harmonics and combined harmonics. So, this omega 0 frequency, here we have the amplitude as 4 by pi, this is the waveform, okay, and 3 omega 0 as amplitude 4 by 3 pi. So, this one. So, if I add up these two, this is what I get basically, okay, and this is the fifth harmonic 5 omega 0, amplitude is 4 by 5 pi, and if I add up this 2, this is what I am going to get, and this is the last one infinite omega 0, amplitude is 0, and if I add it up all these terms. So, this is what I am going to get. So, basically what I am intended to show it here that our square wave signal can be represented in this way basically, okay, that is the by the signal, sinusoidal signal of different frequencies and different amplitude, okay. And as the harmonic frequency increases, the amplitude of the harmonic decreases. This we have already seen. So, the spectrum of a square wave basically this is your Ft. So, plot of unity amplitude square wave with a say DC offset, if this is 1.5 volt, okay, then in the time domain if I plot it, this is how the signal is going to look like, and its spectrum is basically something like this frequencies. So, this is the 0th one, you have the omega 0 frequency, this is basically that 1 by 5 the DC offset basically which I was talking to you, and then you have omega 0 frequency, 3 omega 0, 5 omega 0, 7 omega 0 and so on. So, as you can see that as your frequency increases, their amplitude decreases, and when we sum up all these different terms, basically we get the required signal. Now, let us talk about digital to analog conversion. Okay. The digital to analog converter allows a computer or other digital device to interface with external analog circuit and devices. As I talked to you, these devices could be say the actuator basically, okay. And the simplest type of digital to analog converter is a resistor ladder network connected to an inverter summing operational amplifier circuit. So, that I am going to discuss with you, and this particular converter is a 4-bit R2R resistor ladder network which requires only two precise resistance values, that is R and 2R. and the digital input to the D to A converter is a 4-bit binary number represented by bits say B0, B1, B2 and B3, and where B0 is the LSB or the least significant bit and B3 is the most significant bit, or what we call in short as MSB. So, this is how this R2R ladder network basically comprises of. So, this is your inverting amplifier or operational amplifier, and here you can see that this is a source volt, and you have R here, and you have 2R resistor, 2R here, and this is 2R, and here are the switches basically to switch between the ground and the input to the inverting amplifier here. So, these are the B0, B1, B2, B3 which I talked to you. This B0 is actually the least significant bit, and this B3 represents actually the most significant bit. Okay. And each bit in the circuit controls a switch between the ground and the inverting input of the operational amplifier. So, this is the inverting input as you can see. So, this is how each bit makes a connection to that. Now, to see how the analog output voltage V out is related to the input binary number basically, okay, we can analyze the 4 different input combinations, say 0001, 0010, 0100 and 1000, and apply the principle of superposition for any arbitrary 4-bit number. Okay. And say let us start with the first one. If the binary number is say 0001, the B0 switch is connected to the op-amp and the other bit switches are grounded. Okay. So, as we can see over here. Okay. So, this corresponds to basically 0001. So, here you can see that this one B0 is connected to the op-amp inverting terminal over here, and B1, B2, B3 these are grounded. So, this 001 basically is like this B0, B1, B2 and B3. Okay. So, this is there. Now, with this what happens actually? So, with this because you see the non-inverting input of the op-amp is grounded. Okay. So, the inverting input is also grounded as per the op-amp principle. So, you can see that this is grounded over here. So, this one is also grounded, and this is what we have assumed when we have discussed the operational amplifier. Okay. So, with this if this becomes grounded, then this is how our configuration is basically. So, this R is here, this 2R is here, and this 2R basically becomes something like this. Now, you can see that this 2R and this 2R they are in parallel. So, I can find out equivalent of that, say 1 by x is 1 by 2R plus 1 by 2R. Okay. So, this is basically 1 by x is 2 by 2R, or your x is R basically. Okay. So, the equivalent of this one is basically a resistor of R ohm. Alright. Now, you see here if I take the drop across this resistor is V1 minus V0, okay, and this is also the same resistor. So, that drop is going to be the same, and that is equal to V0 minus this is grounded. So, this is 0. So, from here I can get V0 is equal to V1 by 2. Okay. So, we have V0 is equal to V1 by 2. Similarly, I can have V1 is equal to V2 by 2, V2 is equal to V3 by 2. Okay. And my V3 is nothing but actually this is same as that of the Vs, as you can see in this figure. So, this V3 is same as Vs basically. Okay. So, V0 I can write in terms of V0, that is in this V1 if I substitute this as V2 by 2. So, I get V2 by 4, and if I substitute for V2 as V3 by 2, I get V3 by 8, or this is 1 by 8 of Vs. Okay. And also you see that V0 is the input to the inverting amplifier circuit, and it has a gain of minus RF to R basically. So, feedback resistor to its input resistance. So, R to 2R. So, this is basically minus 1 by 2. Okay. So, that is there. So, the analog output voltage corresponding to binary input 0 0 1 will be what? It will be amplified by half. So, minus half times 1 by 8 of Vs. Okay. So, what does this means? That if your input is 0 0 0 1, okay, your output, that is if for this digital input, your output is going to be minus of Vs by 16. Okay. So, this is what it is going to be. Similarly, if I carry out the similar analysis for an input of 0 0 1 0, my V output 1 is minus Vs by 8. If it is 0 1 0 0, this is minus Vs by 4, and if it is 1 0 0, this is going to be minus Vs by 2. Okay. Now, the output for any combination of the bits comprising the input binaries number can now be found using number can now be found using the principle of superposition as this one. So, V out is basically V3 B3 V out 3 plus B2 V out 2 plus B1 V out 1 plus B0 V out 0. So, this way we have seen how it is done. Then we can have any combinations of we can have the output voltage for any other type of combination using the principle of superposition. Now, if Vs is say 10 volt, the output ranges from say 0 to 15 by 16 into 10 volt for the 4-bit binary input, which has 16 values ranging from 0 0 0 0 which is the 0th one to 1 1 1 1 which is the 15th one. Okay. And a negative reference voltage can be used to produce a positive output voltage range. Okay. And either case yields a unipolar output, which is either positive or negative, but not the both. And if you need a bipolar output that is which ranges over negative and positive values, that can be produced by replacing all the ground references in the circuit with a reference voltage whose sign is opposite to that of the Vs. Next, another very important component is the multiplexer basically, which is a type of switch actually electronic switch device which enable each of the input to be sampled in a term. Okay. So, a multiplexer is a circuit that is able to have input of data from a number of sources, and then by selecting an input channel gives an output from just one of them. Okay. So, it can select a input channel, and for corresponding to that one it can give a output. In application where there is a need for measurement to be made at a number of different locations, okay, rather than using a separate analog to digital converter and microprocessor for each measurement, a multiplexer can be used to select each input in turn and switch it through a single analog to digital converter and microprocessor. Okay. So, the scheme could be like this: you have a signal conditioner unit, there are multiple signals like this, you pass it through a multiplexer over here, there is a channel select channel which can select which channel to be selected, and you have a sampled signal here, and then it can be sent to analog to digital converter, and you get the digital output from over here. Now, you see that in the last lecture I have talked about analog to digital converter. In this lecture I have talked about digital to analog converter. Now, these things are typically available in the form of a data acquisition card. Okay. So, I will like to have a small discussion on USB 6009 data acquisition card. So, the National Instrument USB 6009 is a typical small external data acquisition card that is connected to a computer through a USB port. It has analog to digital conversion capabilities as well as digital to analog conversion, digital input output, and counters as well as timers. The input output lines are connected with wires 16 to 28 AWG to the detachable screw terminals. The screw terminal 1 to 16 are used for the analog input output, and the terminal 17 to 32 are used for the digital input output and counter timer function. Okay. So, here you can see that this 1 to 16 are used for the analog input output, whereas 17 to 32 are used for the digital input output. The USB 6009 provides basic functionality for applications such as simple data logging, portable measurements, and academic lab experiments. The device features a lightweight mechanical enclosure and is bus powered for easy portability. Sensors and signals are connected to the USB 6009 with screw terminal connectivity. The included NI DAQ MX driver and configuration utility simplify configuration and the measurement. The analog terminals are different depending on which mode the device is in: single ended mode, also known as RSE, or different mode. In single ended mode, the positive voltage signal is connected to the an AI terminal, and in the negative voltage or ground signal is connected to the ground terminal. This mode uses two terminal, meaning there are 8 analog inputs available, that is AI 0 to 7, and the maximum voltage range is in this mode is -10 to +10 volt. Differential mode can also be used to get larger voltage range, and this mode measures the difference between the two signals. Okay. So, AI plus and AI minus each reference to the ground. A voltage range of -20 volt to +20 volt can be achieved, but the maximum voltage on one pin, that is AI plus or minus, reference to the ground is 10 volt. Differential mode use one more wire than single ended mode. So, only 4 analog inputs are available in this mode. Another difference between differential and single ended mode is the resolution of the analog input. Differential mode has a resolution of 14 bit, whereas single ended mode has a resolution of 13 bit. The analog input converter type is successive approximation, which I have already discussed with you, and the maximum sampling rate is 48,000 samples per second. these are the further references. If you wish, you can read specifically the Alciator and his stand. Thank you. Okay, I welcome you all in today's NPTEL online certification course on mechatronics. Today I am going to talk about the artificial intelligence. There is much talked about things about artificial intelligence. In fact, there are full-fledged course on artificial intelligence. My aim of introducing this topic to here is to get or make you aware of the use of this concept in mechatronic system. Okay. So, if you are interested, you can refer more on what I am going to discuss in next 30 minutes. Okay. This artificial intelligence these days is used in many of the mechatronic devices. Say people are using it in the washing machine, and people are using in the robotics, and this artificial intelligence, or which is called AI in short, is very useful in taking appropriate decisions. Okay. For example, if I talk about a robot, when the say what the motor speed has to be at which type of situation. Okay. Say if it is climbing, then whether the speed has to be increased or speed has to be decreased. Okay. All those decisions can be taken by say AI. So, dictionary definition of intelligence might be endowed with ability to reason. Okay. The more intelligent we think a person is, more we consider he or she is able to learn, generalize from this acquired knowledge, and be capable of reasoning and able to make predictions by considering what is possible and learning from the mistakes. Okay. So, essentially as I said, let us look at some of the things here. The more intelligent we think of a person is, let us look at what are the qualities basically for to be intelligent. One is that one should be able to learn, and then after learning generalize from this acquired knowledge. Okay. So, generalization of this knowledge, and then capable of reasoning and able to make prediction. Okay, by considering what is possible. Okay, and learning from any mistakes. Okay, and one can apply these concepts to machines as well. Okay, and the intelligent machines are powered with ability to reason. For example, if I talk about say a boiler in a thermal power plant. Okay. So, the question is that should the boiler switch be switched on or off as a result of information from the thermostat? It is not. However, consider it to be intelligent because it is however it is not capable of reasoning and making decision. So, this is not the intelligence, it is not considered to be intelligent. Okay. Because it cannot take decisions over a wide range of condition. Okay. It cannot recognize a pattern in inputs from a thermostat. Okay. And so, it cannot make prediction about whether to switch the boiler on or off. It does not think for itself. If we talk about closed loop feedback system, these systems are actually what we call it as the self regulated system. Okay. In the sense that they regulate the output of a system to a required value. Okay. For example, a thermostatically controlled central heating system of a building say is used to maintain the building temperature at the value set for the thermostat. Okay. Such systems are not considered intelligent as they only do what they were told to do. So, what constitute the intelligence basically what properties the intelligence should have. Okay. So, they should have the awareness or what we call it as the understanding. Okay. They should be able to conclude and act. Actually, they should be have the reasoning and they should be able to think. Next, let us talk about the perception. Okay. Perception basically is collecting the information using sensors. If I am talking about a mechatronic system, okay, I am not talking about the perception considered in other way. For example, say perception of a person. Okay. So, the perception is the collecting of information using sensors and organizing the gathered information so that decision can be made. Okay. So, for example, we may have a control system with a production line where certain part are moving with the help of a conveyor belt or through the conveyor belt, and say we might have a sensor like a video camera, okay, to observe the component. Now, the signals received from the camera enables a computer representation of the component okay, to be made, and so that the features can be identified. And now, these features can be compared with the representation of component in order that the decision can be made about the control system, that whether your components are rightly assembled or not. Okay. So, the action can be taken by the control system to reject a faulty component or divert particular component to a particular boxes. Okay. So, this is what is mean by perception in a mechatronic system. Then is the cognition. Okay. So, once a machine has collected and organized information, okay, that is the perception has been made, it has to make decision about what to do as a consequence of whatever information has been gathered or collected. Okay. And this is termed as cognition. Okay. And vital to this perception and cognition is the pattern recognition. Okay. And what are the patterns in the data gathered, and intelligent machines are able to identify such a pattern. For example, suppose we have an autopilot system on an aircraft. It monitors lot of information, and on the basis of that information, as a pattern, it perceives the data and makes decision on how to adjust the aircraft control. Okay. Machine pattern recognition can be achieved by machine having a set of pattern in its memory, and gathered patterns are then compared with these and a match is sought. Okay. And the pattern in its memory may arise from the model or a process of training in which data is gathered for a range of object or situations, and then the given identification code. Next, let us talk about neural network which is being used in the intelligent machines. Okay. Such network do not need to be programmed, but can learn and generalize from examples and training. Okay. And a neural network is composed of a large number of interconnected processing units, and the output from some units being input to the other unit. Okay. And each processor in the network receives information at its input and multiplies it by a weighing factor basically. Okay. So this is what is done. So we could have a network something like this, where you have the inputs from here, okay, and certain processes are being taking place here, and then you get the output from this side. Okay. And here in the processes basically you can have the various weights. Okay. So if operating as and it then sums these weight input and give an output of say 1 if the sum exceeds a certain value, or say it is positive. So, for example, we might have an input of 1 with a weighing factor of say minus 1.5. So, this will be giving me 1 into minus 1.5. So, that is minus 1.5. Another input with 1 with a weighing factor 1, and another give input 1 and that give 1, and third input 1 with a weighing factor 1, okay, giving 1. Okay. So, this way basically what I have is that input 1 with weighing factor say minus 1.5, another input 1 with weighing factor 1, and another input 1 with weighing factor 1. Okay. So, this will be actually giving me a value say 0.5. So, say this is a positive value. So, I can take it as say represent that positive value by 1. Okay. So, as I said the sum of these weight could be 0.5. So, an output of 1 if these values are positive for an output. Okay. Similarly, if I have input say as 1 0 0, okay, so in that case my output will be say 1 into 1 minus 1.5, 0 into 1 and 0 into 1. So, this is minus 1.5. Okay. So, I could have an output of 0. So, this is how basically a neural network works. Okay. So, the network can be programmed by learning from example, and so be capable of learning. Next thing in AI is actually the reasoning. Okay. And reasoning is the process of going from what is known to what is actually not known. Okay. There are number of mechanisms to carry out the reasoning, and these mechanism could be deterministic reasoning, and these could be using say if then type of statement or if then type of rule which we conventionally use in any of the programming. coming. Okay. Suppose we might deduce that say if a coin has diameter of say 1.25 centimeter, then it is a pound coin. Okay. So, this type of deterministic reasoning using if and then could be formulated, okay, and this is what we call it as the deterministic reasoning. And if the first part of the statement is true, then the second part of the statement is true. If the first part of the statement is false, then the second part is not true. Okay. So, in this form of reasoning we have say the true false type of situation. So, that type of thing also can be formulated. Then the other type of reasoning is the non-deterministic reasoning, and this allows to make the predictions based on the concept of probability. Okay. For example, suppose if I toss a coin, there are only two ways it can land, okay, say face upward or face downward. So, out of the two ways there is just one way which will give the face upward. Okay. So, the probability of its landing face upward is 1 into or 1 by 2. So, I can have the heads probability as 1 by 2 and I can have the tails probability as also 1 by 2. Okay. And suppose I can take another example, say throwing of a 6-sided die. Okay. Then the probability of its landing with a 6 uppermost is the 1 by 6. Okay. And this is how we can see. So, the probability for each type of face landing of each type of face is basically 1 by 6, and the total probability in this case will be 1. Okay. So, these type of for the non-deterministic type of the non-deterministic type of reasoning, we can use the concept of probability to make the prediction, and for deterministic type of reasoning we can use the if then or the true false type of situation in order to do the reasoning. Okay. Then we could also have the rule based reasoning. Okay. So, at the heart of the rule based reasoning are a set of rules basically. Okay. And these rules when combined with say input from sensors and user enable inferences to be made which are then used to actuate your actuator and the get the control output. Okay. And the combination of the fact and rule database is known as the knowledge base for a machine. Okay. So, you have essentially the fact database as well as the rule database, and this is what is known as the knowledge base for a machine. Okay. So, in the rule based reasoning basically it is something like this. So, you have the user input, okay, and you have the sensor input. Okay. So, user input is fed through user interface, sensor input is fed through the sensor interface. Okay. So, that is there, and then these input are sent to the knowledge base, and this knowledge base consists of the fact database as well as the rule database. Okay. And from this we carry out the inferences, okay, and from the inferences we send the or the actuator interface is there connected, and of course, this interface will be working on the actuator, and you have the processes and output. So, inference is where reasoning takes place as a result of the input fact being combined with the rules and decision made, which are then fed to the actuator. Okay. The rules used are often in the form of if then statement, Thus, we might have a group of rules say for a central heating system of the room. Okay. So, it could be something like this: if boiler is on, then your pump is on. If pump is on and the room temperature is say less than 20 degree, then open the valve, and if its boiler is not on, then your pump is not on. So, this type of rule base we can have, okay, here. And the fact database, I have talked about two things over here in the knowledge base, the fact database and the rule database. Okay. So, here I just talked about the rule thing where we are using the if then statement, and the fact database we could have the facts. Okay. For example, room temperature say less than 20 degree. Okay, timer is on, valve is open, boiler is on and pump is on. Okay. So, we could have these type of the fact database. Okay. And the rules can also be in the form of propositions involving probability statement, or it could be in the form of fuzzy logic. Okay. So, this is what I talked about the rule based reasoning. Okay. So, next let us see the fuzzy logic. Okay. So, fuzzy logic also helps us in designing the intelligent systems. Okay. So, it was Lotfi-Jade proposed in 1965 a form of reasoning which has become what is popularly known today as the fuzzy logic. And one of the main idea here is that things could not be classified as true or false, okay, but their truth or falsehood can be weighted so that it can be classified between the two on a scale. So, for example, before we proceed further, let us look at some fewer concepts of the fuzzy logic. Say consider say this statement, say April 1st was supposed to be very warm day in IIT Roorkee, and in fact it turned out to be pretty hot. Okay. So, here you see that I have used the warm, very warm and pretty hot. Okay. So, these are not the crisp values, these are not the exact values, okay, to indicate the state of weather. Okay. So, here things are not certain, things are not clear. Okay. So, for example, if I say that it is warm, somebody may ask what temperature it is. Okay. So, the description, this type of description is what is of temperature is what is called as fuzzy. So, fuzzy description of event and other phenomena are context dependent. Okay. For example, say if somebody has got an accident. Okay. So, if it is a young child, its description of hurt because of the accident could be different than the description given by an adult. Okay. So, this fuzzy description and events are also the context dependent. Now, to explain the concept of fuzzy logic, I will take up an simple example. Basically, here say a cooling system to be controlled by fuzzy logic. Okay. The two inputs are say temperature and humidity, and the output is the power setting of the say air conditioning system. And suppose we need to design a fuzzy logic control system for such a system. Okay. Now, here actually what we have to do is that what are our inputs? Inputs are, we have basically the temperature and humidity, and output is the power setting of the air conditioning system. Okay. So, here the first process in any fuzzy logic control, first is the basically fuzzification. Okay. So, here what we do actually, with temperature we mention the degree of say membership. Okay. Here temperatures are mentioned in Fahrenheit. So, here I could have the 4 conditions for the temperature, say very hot, warm and cold. Okay. So, this way I can define over here. Okay. And for the humidity also similarly, say I could have the 3 classification, that is dry, humid and very humid, and my output, that is the percentage of power could be say a off condition, slow, medium and fast basically. Okay. So, this process is what we call it as the fuzzification. Okay. So, here I have considered their variations as the triangular variation. Okay. And then the next step after fuzzification is the development of the rule base. Okay. So, basically here you can see that we have 4 states here for the temperature and 3 for the humidity. So, I am going to have the 12 rules basically. Okay. That is 4 into 3. So, all the possible combinations. So, say rule 1 could be, if temperature is very hot and humidity is very humid, then the power has to be fast. Okay. So, rule 2 could be, say if temperature is very hot and humidity is humid, then power is fast. Okay. So, this way we could generate the rule bases. Okay. So, say the last one could be, if temperature is cold and humidity is dry, okay, and then the power has to be off. Okay. That is your air conditioner should not work. Okay. So, after this rule base, okay, what we could do is that we could to make the decisions. Okay. Say we can draw a diagram like this, where say we have the temperature conditions mentioned over here and humidity condition mentioned over here, and these are our output. Okay. And here are the rules basically. So, I have 1 to 12 rule which has been generated. Okay. So, suppose say the present temperature is 78 degree Fahrenheit and say humidity is 70%. Okay. So, for 78 degree Fahrenheit temperature, actually the resulting membership values will be 0.7 warm, 0.27 hot and 0.65 humid. Okay. So, this is going to be there, and all other membership values are going to be 0. Okay. So, as I was telling, for 78 degree temperature, say corresponding to hot, you have this value as 0.27, and corresponding to warm you have a value as 0.7. Okay. So, that is there. Okay. And for 70% humidity, here you are going to have this value as 0.65, and all other membership are going to be 0. Okay. So, then we can substitute or we can put these values over here. Okay. Say for example, for humid this is 0.65, okay, for warm this is 0.7, and for hot it is 0.27 over here. Okay. So, these values could be put, and for all other these values are that is very hot is 0, very humid is 0 and dry is 0. Okay. Then based on these rule base we could generate the output. Okay. So, based on this rule base from R1 to R12 the output could be generated. Okay. So, substituting these values into the corresponding rules, output membership values are actually 0.27 medium and 0.65 slow. Okay. So, we get here to 0.27 medium and 0.65 slow. Since we are using AND logic, minimum value between the numbers is chosen. Okay. So, that is there, and the last step on this is the defuzzification, because ultimately we want a certain value for the air conditioner, that is at what power setting it has to run. Okay. So, this value the 0.27 and 0.65 this which we have evaluated over here from this rule base, these values which we have evaluated, these values could be put into here, and using the CG method we can derive what power setting is going to be. Okay. There could be another way of doing that, and that method is what we call it as the Mamdani's inference method, okay, where we calculate the CG of the resulting area by taking the first moment of area and dividing it by total area. So, that will be coming around 34% of the power rating. So, this way you can see that we apply the fuzzy logic, okay, in taking or making an intelligent decision about the setting of the power, okay, for the air conditioner. Now, these fuzzy logic concepts are very much used in the domestic washing machines, where they can sense the fabric type, how much dirt is there in your fabric, and what is the load size, and adjust the wash cycle accordingly. Okay. It could also be used in controlling the robot and adding intelligence to it. For example, say we have the mobile robot designed for rough terrain. Okay. So, in that case a fuzzy logic controller can be used to enhance the robot controller, okay, in decide what action to be taken depending on say the speed of the robot, the terrain, and the robot power. In industrial robots which are handling an object, say an end effector must exert a force proportional to two other inputs, say the size of the part and its weight. Okay. So, there we can use this fuzzy logic. Then we can also use it in say case of sorting of bags. Okay. So, a robot is used to sort a bag of object based on their color according to say the color of rainbow. Then now let us see about learning. Okay. So, the machine that can learn and extend their knowledge base have greater advantage compared to with machine that cannot learn, and learning can be thought of as adapting to the environment based on the experience. Okay. And with machines learning can be accomplished in a number of ways. A simple method of learning is by the new data being inputted and accumulated in the memory. Okay. Machine can also learn by the data they receive being used to modify parameters in the machines. Okay. Another method of learning that can be used is when reasoning is defined in terms of probabilities, and that is to update the probabilities used in the light of what happens. So, for example, say we have a bag containing 10 colored balls, okay, and all being blue apart from one black. Okay. Now, when we draw a first ball from the bag, the probability of the pulling the black ball out of is 1 by 10. Okay. If we find it is a blue ball, then the next time we draw a ball, the probability is going to be 1 by 9. So, our machine can learn from the first ball being red by adjusting its probability values for the black ball being drawn. Okay. So, base rule to update a machine is say P H E is P E H cross P H by P E. Okay. So, here H is the hypothesis that we start with E and example now encountered. So, P H E is the probability of the hypothesis H being true given that the example A has happened. P E H is the probability of the example E happening giving that the hypothesis H is true, and P is the probability of example E happening. Okay. P H is the probability of the hypothesis H being true. Okay. So, this allows the machine to update the probability of H every time new information occurs. Yet another method a machine can learn is from the examples, okay. And this is when a machine generalizes from set of examples. These may be the result of training with example being studied to the machine, so that it can build up its rules or as a consequence of event it has encountered. So, pattern recognition generally involves a form of learning, okay, and neural network also involves learning by example. So, looking at the applications of AI. So, this is used in the various appliances, robotics, science, search engines and medicine and diagnosis. So, in applications it is used in the image processing, pattern or recognition for example, from speech or vision, data mining, robotics, computer or wireless network, natural language processing or others. Okay. And why do we are looking for the intelligent system? Okay. So, to understand the motivation for using intelligent system, to recognize computational approaches to intelligence, to master the basic design methodology for intelligent system, to understand the motivation for using artificial intelligence system, and to use intelligence system for solving problem in the domain of informatics and engineering. So, this is the reference. You can refer Bolton for mechatronics, and for the fuzzy example which I have shown, you can refer robotics by Niku. Okay. So, thank you very much.